Long before humans existed, Earth's oceans were ruled by enormous and powerful marine creatures. More than 500 million years ago, early sea life began to grow larger and more complex. During the Devonian period, giant armored fish like Dunkleosteus dominated the waters. Later, in the age of reptiles, massive swimmers such as Ichthyosaurus and Mosasaurus became top predators. Some stretched longer than 50 feet and controlled vast marine territories. These forgotten ocean giants shaped ancient ecosystems for millions of years before disappearing during major extinction events, leaving behind fossils that reveal a powerful and fascinating chapter of Earth's distant past. Dunkleosteus was a massive, armored fish that lived during the late Devonian period, roughly 382 million to 358 million years ago. It belonged to a group of ancient fishes called Arthrodires, meaning jointed neck, because the bony plates around the head and body were connected in a way that allowed movement. Unlike many earlier fish, it did not hide near the sea floor. It swam in open ocean waters, moving through deep, wide seas as a powerful hunter. In fact, it was one of the earliest backboned animals to sit at the very top of the food chain in its environment. Fossils of this fearsome predator have been discovered in what are now the United States, Canada, Poland, Belgium, and Morocco, showing that it once ruled large parts of the ancient world's oceans. Scientists currently recognize about 10 different species within this genus. Some of these species are believed to have been among the largest of all placoderms, a group of early fishes known for their thick, bony armor plates that covered their heads and upper bodies. These species include Dunkleosteus terrelli, Dunkleosteus belgicus, Dunkleosteus denisoni, Dunkleosteus marsaisi, Dunkleosteus magnificus, Dunkleosteus missouriensis, Dunkleosteus newberryi, Dunkleosteus ambliodoratus, Dunkleosteus raveri, and Dunkleosteus tudorensis. However, paleontologists are still debating whether all of these truly belong to the same genus. Some fossils are incomplete, and certain species may actually be duplicates of others that were named separately in the past. The largest and most famous species is Dunkleosteus terrelli, which serves as the main example, or type species, for the entire genus. Because no complete skeleton has ever been found, scientists do not know the exact body shape of Dunkleosteus. Most fossils consist mainly of the heavy armor plates from the head and front part of the body. As a result, researchers have had to estimate its total length and weight by comparing it with other fish and by using mathematical models. Earlier estimates suggested that the largest known individual of Dunkleosteus terrelli might have reached lengths between 4.1 and 10 meters, with a weight between 1 and 4 metric tons. However, more recent and detailed studies suggest that such extreme sizes were likely overestimated. Current research indicates that most adult individuals were probably around 3.4 meters long, while especially large ones may have reached about 4.1 meters. Even at these more moderate estimates, Dunkleosteus would still have been an enormous and intimidating predator. One of the most fascinating features of Dunkleosteus was its jaw. Unlike modern sharks, it did not have true teeth. Instead, it had sharp, bony plates that formed blade-like edges. These plates could slice through flesh and crush bone. For many years, scientists believed that Dunkleosteus could open and close its jaws with incredible speed, possibly creating a strong suction force to pull prey into its mouth, similar to certain modern fish that feed by suction. It was also once thought to have one of the strongest bite forces of any fish that ever lived. More recent studies, however, have questioned how powerful and how fast its bite truly was. While it was undoubtedly a formidable predator, some earlier claims about its abilities may have been exaggerated. The story of Dunkleosteus began in the year 1867 when a hotel owner and amateur fossil collector named J. Terrell discovered strange armored plates in cliffs along Lake Erie near Sheffield Lake, Ohio. He donated his finds to John Strong Newberry and the Ohio Geological Survey. In the year 1873, Newberry described the fossils as belonging to a single new genus and species, which he named Dinichthys. However, as more fossils were uncovered from the same region, especially from layers of rock known as the Ohio Shale, it became clear that several large species of armored fish had lived there. By the year 1875, Newberry recognized that many of the fossils came from a different and more common species found in a younger rock layer called the Cleveland Shale. He named this species Dinichthys terrelli in honor of J. Terrell. Sadly, most of Terrell's original fossil collection was destroyed in a fire in Elyria, Ohio, in the year 1873. Today, the largest collection of Dunkleosteus fossils in the world is housed at the Cleveland Museum of Natural History. Other important collections can be found at the American Museum of Natural History, the Smithsonian National Museum of Natural History, the Yale Peabody Museum, the Natural History Museum, and the Cincinnati Museum Center. Many of the mounted displays seen in museums around the world are casts made from a single especially well-preserved specimen known as CMNH 5768. The original fossil of this specimen remains on display in Cleveland. In the year 1956, the French paleontologist Jean-Pierre Leman officially gave the genus its current name, Dunkleosteus, in honor of David Dunkel, who served as curator of vertebrate paleontology at the Cleveland Museum of Natural History. The name combines Dunkel's surname with a Greek word meaning bone, so it literally translates to Dunkel's bone. At first, scientists believed Dunkleosteus was closely related to the genus Dinichthys, and they grouped them together in the same family. Later studies of their features and evolutionary relationships showed that they actually belong to separate branches within the Arthrodire fishes. Research published in the early 21st century found that Dunkleosteus belongs to a group called Dunkleosteoidea, while Dinichthys belongs to a different and more distant group. As a result, scientists revived a family called Dunkleostidae to include Dunkleosteus and some related genera, separating them more clearly from other armored fishes. However, ongoing studies using larger sets of anatomical data have continued to debate exactly how these groups are related, and the classification of these ancient fishes remains an active area of research. Although at least 10 species of Dunkleosteus have been described, many are based on fragmentary remains, such as single plates or jaw bones. Some may eventually be shown to belong to other genera, or to be the same as species already named. In some cases, the name Dunkleosteus has been used as a kind of catch-all category for large armored fishes that resemble it, but are not yet clearly understood. The best-known species, Dunkleosteus terrelli, is also the largest and most thoroughly studied. Its skull plates alone can measure up to 60 to 70 centimeters in length. Fossils of this species have been found in late Devonian rock layers in several parts of the United States, including Ohio, Pennsylvania, Tennessee, California, and possibly Texas, as well as in parts of Europe. These discoveries show that Dunkleosteus terrelli lived in a wide range of marine environments during the final chapters of the Devonian period. Other species vary in size and form. Dunkleosteus belgicus is known from fragments found in Belgium, but some scientists believe the material may actually belong to another genus. Dunkleosteus denisoni is identified from a smaller dorsal plate, while Dunkleosteus marsaisi, found in the Atlas Mountains of Morocco, has narrower skull features and may or may not be a distinct species. Dunkleosteus magnificus, originally described under a different name from New York, had a skull about 55 centimeters long and may have reached a total length of around 3 meters. Dunkleosteus missouriensis is known from fragments in Missouri and may simply represent another example of Dunkleosteus terrelli. Dunkleosteus newberrii is mainly known from a jawbone about 28 centimeters long, discovered in New York. Interestingly, it has a longer row of cutting edges than other species and lacks certain small, tooth-like structures, raising doubts about whether it truly belongs within Dunkleosteus. Dunkleosteus ambliodoratus from Ontario is named for the spear-like shape formed by certain head plates. Dunkleosteus raveri was a smaller species, possibly about 1 meter long, with relatively large eyes, and may have been an ancestor of Dunkleosteus terrelli. Finally, Dunkleosteus tudorensis is known from a lower jaw plate found in what is now northwestern Russia, named after the Mali Tudor River where it was discovered. Taken together, these fossils paint a picture of a powerful and widespread predator that dominated ancient seas hundreds of millions of years ago. Even though much about its true shape and lifestyle remains uncertain, Dunkleosteus continues to capture the imagination as one of the most impressive armored fishes ever to live. Out of the roughly 10 named species that have been linked to Dunkleosteus over the years, only 4 are fully accepted by most scientists today as true and valid members of the genus. These are Dunkleosteus terrelli, Dunkleosteus raveri, Dunkleosteus tudorensis, and possibly Dunkleosteus ambliodoratus. Even among these, there are still questions. For example, some fossils found in Morocco may or may not truly belong to Dunkleosteus terrelli. Dunkleosteus ambliodoratus is known from only a small amount of fossil material. The bones look different enough to suggest it is its own species, but there is not enough evidence to compare it properly with other close relatives. This makes it difficult to be completely certain. The classification of species from the earlier part of the late Devonian period, especially during the Frasnian age, is still unclear and debated. Fossils from this time are harder to sort and identify with confidence. However, species from the very end of the Devonian period, during the Furmenian age, are much easier for scientists to assign to the genus Dunkleosteus. In addition to the 4 widely accepted species, there are also fossil fragments labeled simply as Dunkleosteus species from Furmenian rock layers in places such as California, Texas, Tennessee, and Poland. These fossils are not complete enough to name as new species, but they show that Dunkleosteus had a wide geographic range. One of the most striking features of Dunkleosteus was its heavy armor. Its head and the front half of its body were covered in thick plates of dermal bone that formed a kind of natural shield. Many descriptions claim that this armor was more than 2 to 3 inches thick. However, this thickness only applies to a specific part of the skull called the nuchal plate, located at the back of the head. This plate was especially thick and reinforced, which is common among a group of armored fishes known as eubrachithoracid arthrodires. The rest of the armor covering the body was much thinner, usually between about 1/3 of an inch and 1 inch thick. Even though thinner than the nuchal plate, this armor was still strong and protective. The bone structure of these plates was also unusual. They had a dense, hard outer layer and a spongy inner layer filled with marrow. This structure is more similar to the bones of 4-limbed animals than to most modern bony fishes. Most modern teleost fishes have lighter, simpler bone structures. Dunkleosteus, by contrast, had plates that were thick, layered, and built for strength. Unfortunately, most Dunkleosteus fossils preserve only the armored front sections of the body. The back half of the fish, including much of the tail, is rarely found. In fact, only about 5% of known specimens preserve more than 1/4 of the entire skeleton. Because of this, scientists must often rely on related but smaller armored fishes, such as Coccosteus, to guess what the missing parts of Dunkleosteus looked like. Since these relatives were much smaller and had slightly different proportions, this has led to many different size reconstructions over the years. Dunkleosteus terrelli is considered one of the largest placoderms ever discovered. However, estimates of its maximum length vary widely. Some researchers have suggested lengths between about 4.1 meters and 10 meters. These large numbers have often been repeated, but many of them are speculative and not backed by detailed measurements or statistical analysis. Lengths of 5 meters or more are especially uncertain and poorly supported. Many studies that provide large size estimates do not clearly explain how those numbers were calculated. Lengths of 5 meters or more are especially uncertain and poorly supported. Many studies that provide large size estimates do not clearly explain how those numbers were calculated. They often fail to state which fossils were used or how the measurements were scaled. Most of these reconstructions are thought to be based on two main fossil specimens. One is CMNH 5768, which preserves the largest complete armor set known for Dunkleosteus terrelli and has a skull length of 61.3 centimeters. The other is CMNH 5936, which consists of a very large jaw fragment. However, to reach the biggest length estimates, these reconstructions often require Dunkleosteus to have body proportions that are unlike those of other arthrodires, such as Kronosaurus or Amazicthys. This creates further doubt. The most detailed and careful studies of body size suggest that a typical adult Dunkleosteus terrelli was about 3.4 meters long. Only very rare and exceptional individuals may have reached about 4.1 meters in length. These estimates were calculated using several different measurement methods, including head length, the length of the head without the snout, the length of the ventral shield, the angle of the armor plates, and the positions of the pectoral and pelvic girdles compared to the total body length. When different methods give similar results, scientists gain more confidence in the numbers. Even when accounting for statistical margins of error, typical adults might possibly have reached about 3.7 meters, and exceptionally large individuals might have reached about 4.5 meters. However, anything larger than this would give the fish body proportions that do not match other known arthrodires or jawed fishes. In particular, the head and trunk armor would appear far too small compared to the total body length, and the positions of the fins would not align with what is seen in related species. In fact, even the upper limits of these error ranges may already be slightly generous. On the other hand, estimates much smaller than 3.4 meters are unlikely because the preserved armor itself already measures close to those dimensions. Most well-supported scientific studies conclude that Dunkleosteus terrelli was 5 meters long or less. One major exception is a study published in 2017 by Ferron and colleagues, which estimated a length between 6.88 meters and 8.79 meters. These estimates were based on comparisons between the upper jaw perimeter of Dunkleosteus and those of modern sharks. However, arthrodires like Dunkleosteus have proportionally larger mouths than modern sharks. This means that using shark measurements likely overestimates their body length. When this same jaw-based method is applied to complete arthrodires such as Kronosaurus, it also produces body lengths that are too large. Furthermore, the reconstruction proposed in the 2017 study would give Dunkleosteus an unusually small head and an extremely long trunk compared to what the fossils actually show. When their model is properly scaled to match the known dimensions of specimen CMNH 5768, the total body length becomes about 3.77 meters, which agrees closely with later and more conservative studies. Weight estimates have also changed over time. In 2010, Carr estimated that a 4.6 meter long adult Dunkleosteus terrelli might have weighed about 665 kilograms, assuming a body shape similar to that of a shark and a similar relationship between length and weight. More recently, in 2023, Engelmann used a method that models the body as a three-dimensional ellipsoid to calculate volume. This approach estimated that a typical adult measuring about 3.41 meters would have weighed between 950 and 1,200 kilograms. For the largest individuals in that study, measuring about 4.1 meters, the estimated weight ranged from 1,494 to 1,764 kilograms. These heavier estimates reflect the fact that Arthrodires had deeper and wider bodies than most sharks, making them bulkier animals. One remarkable fossil of Dunkleosteus torelli preserves the outline of a pectoral fin, including structures called ceratotrichia that supported the fin. This discovery showed that placoderm fin shapes were more varied than scientists once believed. It also suggested that fin shape was strongly influenced by how the animal moved and hunted, rather than strictly by its evolutionary relationships. Using this new understanding, a study in 2017 reconstructed the tail fin of Dunkleosteus torelli in a new way. Instead of having a long, eel-like tail as once thought, it likely had a powerful tail with a strong lower lobe, a narrow base where the tail met the body, and a high aspect ratio shape suited for active swimming. This design would have made it a fast and efficient predator. Very little of the vertebral column has been preserved. The only known vertebral remains consist of a small series of 16 vertebrae found inside the trunk armor of specimen CMNH 50322. Many of these vertebrae are strongly fused together and have large side-facing joints compared to other arthrodires. While some related species show partial fusion of front vertebrae into a structure called a synarcual, the fused region in Dunkleosteus extends almost to the end of the trunk armor. This suggests that its spine was extremely stiff. There is also a ridge on the inside of the trunk armor that indicates a strong attachment point for a structure called the horizontal septum, which separates muscle groups. This suggests that Dunkleosteus may have had a reinforced front body and specialized connective tissues that transferred powerful muscle forces from the front of the body to the tail. In this way, it may have functioned somewhat like modern fast-swimming fishes, such as lamnid sharks and tunas, which use stiffened bodies and strong tails to generate high-speed bursts. All of this evidence paints a picture of Dunkleosteus not as a slow, lumbering giant, but as a heavily armored, muscular and highly capable predator of the Devonian seas. The pelvic girdle of Dunkleosteus was surprisingly small when compared to the massive armored plates that covered the front half of its body. Even though this fish could grow to an enormous size, the bones that supported its rear fins were not nearly as large or heavy as the thick head and chest armor. Several fossils still preserve these pelvic girdles attached to the rest of the skeleton. Unfortunately, when these fossils were first collected, scientists did not carefully record the exact position of the pelvic bones in relation to the armor. This makes it harder to know precisely how everything was arranged in life. However, most of these fossils were dug out of steep cliff faces, and the pelvic bones were found very close to the armor plates. That strongly suggests that the pelvic fins were attached near the back end of the belly shield, much like in other armored fishes known as arthrodires. In one fossil, researchers even believe they can see the base bones of the pelvic fins located close to the end of the trunk armor, giving more clues about how the fins were positioned. One of the most fascinating species, Dunkleosteus torelli, had an extraordinary jaw system. Instead of a simple hinge like many animals, its jaws worked through a complex 4-bar linkage mechanism. This system connected the skull, the heavy chest armor, the lower jaw, and the powerful jaw muscles through a series of movable joints. When one part moved, the others moved in a carefully coordinated way. Computer models created by scientists suggested that this mechanism allowed the jaws to snap open with incredible speed. According to these studies, the mouth could open in about 20 milliseconds, and the entire motion of opening and closing could be completed in roughly 50 to 60 milliseconds. That speed is similar to modern fishes that use suction feeding, where they quickly expand their mouths to pull prey inside with a rush of water. But speed was only part of the story. The bite force of this animal was astonishing. Estimates suggested that the pressure at the tip of the jaw could reach more than 4,000 newtons, and even higher along the sharp blade edges of its bony jaw plates. Some calculations proposed forces exceeding 6,000 newtons at the tip and more than 7,000 newtons along the blade. If accurate, this would make its bite the strongest ever measured in any living or extinct fish, and among the most powerful bites of any animal known. The pressure created by such force would have been strong enough to pierce or slice through tough outer coverings and body armor. This suggests that it was well adapted to attack and break open armored, free-swimming prey, including shelled creatures such as ammonites and even other armored fishes. However, not all scientists agree with the idea that this fish relied heavily on suction feeding. In 2025, researchers led by Engelmann re-examined these earlier models and raised important questions. They argued that some of the assumptions used in the computer simulations may not accurately reflect the true anatomy of the animal. The blade-like jaw plates of Dunkleosteus look more like those of active predatory fish that chase down prey, bite with a wide open mouth, and then tear their victims into pieces. This is very different from modern and ancient suction-feeding jawed vertebrates, which usually have smaller mouth openings and tightly packed brush-like teeth designed to grip rather than slice. Suction feeders also often have special structures that limit how wide their mouths can open. A very large mouth, like that of Dunkleosteus, would actually reduce the strength of suction because the water would not be pulled in as efficiently. Engelmann and his team also pointed out that Dunkleosteus lived in open ocean waters. In such an environment, using suction to capture large prey would not always be reliable because water resistance can weaken the suction effect. They proposed that the skull of this animal may have contained more cartilage than previously believed. Much of the major jaw connections and muscle attachment areas might not have been solid bone, but flexible cartilage. This would have allowed the mouth to open to an extremely wide angle, possibly between 65 and 70 degrees. If this new interpretation is correct, then the earlier bite force estimates may need to be carefully reviewed and recalculated. There is also direct fossil evidence that gives clues about its diet. Teeth from a type of cartilaginous fish known as Oridus were found together with remains of Dunkleosteus. Scientists think these teeth were likely part of stomach contents that had been regurgitated. Oridus is believed to have been a fast-swimming open ocean fish. If Dunkleosteus was able to catch such quick prey, then it must have been a powerful and capable swimmer itself, not the slow, clumsy giant that some earlier researchers imagined. Many Dunkleosteus fossils are found with compact masses of fish bones nearby. These appear to be partly digested remains that were vomited back out. This suggests that it often swallowed prey in large chunks and later expelled the indigestible bones rather than fully breaking them down. As Dunkleosteus matured, its lifestyle may have changed. Young individuals probably lived in shallower waters where food was plentiful and predators were fewer. Adults, like many other placoderms, may have moved into deeper marine environments. Some fossils even show damage that looks like puncture wounds made by the sharp, bony jaws of other Dunkleosteus. This hints at violent encounters, possibly fights between rivals or even cannibalism. Reproduction in Dunkleosteus may also have been advanced for its time. Together with many other placoderms, it might have been among the earliest vertebrates to use internal fertilization, similar to some modern sharks. Fossils of related armored fishes have shown evidence that they gave birth to live young and may even have had structures resembling an umbilical cord. If Dunkleosteus shared this trait, it would mean that complex reproductive strategies evolved much earlier in vertebrate history than once thought. Studies of juvenile lower jaws of Dunkleosteus terrelli reveal another surprising detail. Even young individuals had jaws that were thick and strong in proportion to their size. They were not delicate or weak compared to adults. This means that even at a young age they were already capable of delivering powerful bites and slicing into tough prey, though on a smaller scale. This pattern is very different from what we see in many four-limbed animals today, where juveniles usually have slimmer, weaker jaws that only become robust as they grow. In Dunkleosteus, strength came early, suggesting that from youth to adulthood it was built to be a predator. Basilosaurus, whose name means king lizard, was not a lizard at all, but a massive early whale that ruled the seas during the late Eocene epoch, roughly between 41 and 34 million years ago. When it was first described in the year 1834, it became the very first ancient whale of its kind ever recognized by scientists. At that time, knowledge about prehistoric sea mammals was still limited, and the strange bones that had been discovered confused the experts. The first fossils of the main species, Basilosaurus sitoides, were found in the southeastern United States. Because the bones were enormous and unusual, the scientist who studied them believed they belonged to a giant marine reptile. That is why the creature was given the name king lizard. Later research proved that the animal was not a reptile at all, but an early, fully marine mammal. Scientists attempted to change its name to better reflect its true identity, but the rules of scientific naming require that the original name must remain, even if it was based on a mistake. So the misleading name stayed. A second species, Basilosaurus isis, was officially named in the year 1904. Its fossils were discovered in North Africa and in Jordan, in areas that were once covered by the ancient sea that later became part of the Mediterranean region. These discoveries showed that Basilosaurus was not limited to North America. It had spread across vast, warm seas that once covered large parts of the world. Basilosaurus was one of the largest animals of its time during the Paleogene period. The main species could grow to a length of about 17 to 20 meters, which is roughly 56 to 66 feet, and it may have weighed as much as 15 metric tons. That made it one of the top predators in its shallow inland seas. It hunted sharks, large fish, and even other marine mammals. One of its most common prey animals appears to have been its smaller dolphin-like relative, Dorudon. Fossils of Dorudon have been found with clear bite marks that match Basilosaurus teeth, and in some cases Dorudon bones were even discovered inside the stomach contents of Basilosaurus skeletons. This paints a vivid picture of a powerful hunter dominating ancient coastal waters. For many years, Basilosaurus became what scientists call a wastebasket taxon. This means that many different whale fossils from the Eocene were placed into this genus simply because they looked somewhat similar. As research improved and more complete skeletons were discovered, scientists carefully re-examined these fossils. Over time, most of those species were removed and assigned to other genera. Today, only 2 species are widely accepted as true members of Basilosaurus. Basilosaurus may have been among the first whales to live completely in the open ocean, sometimes grouped within a broader category known as Pelagiceti. Unlike modern whales, which usually have uniform teeth and swallow their food whole, Basilosaurus had different types of teeth in its mouth. It had sharp canine-like teeth and grinding molars, a condition called heterodonty. This suggests that it could bite, tear, and chew its prey, rather than simply gulping it down. The story of its discovery is dramatic. In Louisiana, heavy rain once caused a hillside filled with seashells to collapse, exposing a long, curved line of enormous bones stretching for more than 120 meters. Some local people even used a number of these giant bones as fireplace supports, not realizing their scientific value. Fortunately, several important pieces were saved and eventually studied. The fossils made their way to the American Philosophical Society and into the hands of the anatomist Richard Harlan. Seeing the massive vertebrae, Harlan believed he had discovered a gigantic marine reptile. He compared the bones to creatures such as Plesiosaurus and Mosasaurus, and even to large dinosaurs like Megalosaurus and Iguanodon. Based on the size of the vertebrae, he estimated the animal could have been between 24 and 30 meters long, far larger than we now believe it actually was. Convinced it was a reptile, he named it Basilosaurus. Later, the fossils were shown to the British anatomist Richard Owen. Owen carefully studied the teeth and noticed something important. The molars had two roots, a feature not found in reptiles or fish, but typical of mammals. From this, he correctly concluded that the animal was a whale. He suggested renaming it Zeuglodon cetoides, meaning whale with yoke-shaped teeth, referring to its double-rooted molars. However, since Basilosaurus had already been officially published, the original name could not be replaced. Important discoveries were also made in Egypt, especially at Wadi El-Hitan, whose name means Valley of the Whales. This desert area was once covered by sea and is now famous for its rich deposits of early whale fossils. In the late 19th century, researchers began uncovering Archaeocete remains there. Over time, hundreds of skeletons were discovered, many belonging to Basilosaurus isis and Dorodon atrox. Some Dorodon fossils even showed bite marks that matched Basilosaurus, confirming their predator-prey relationship. In the 1980s, paleontologists including Elwin L. Simons and Philip D. Gingerich carried out major excavations in the Egyptian desert. Since then, more than 500 early whale skeletons have been uncovered from the region. Some Basilosaurus fossils included small hind limbs, much reduced compared to land mammals. These tiny back legs were likely not used for walking, but may have helped during mating. In the year 2015, scientists uncovered the first nearly complete Basilosaurus skeleton at Wadi El-Hitan. Even more remarkable, it was preserved alongside the remains of its prey, including Dorodon and several fish species. The skeleton also showed signs that large sharks, such as the otodontid Otodus sokolovi, had scavenged parts of the carcass after its death. Some researchers even suggested that such sharks might have been part of Basilosaurus's own diet while it was alive. Altogether, Basilosaurus represents a powerful and fascinating chapter in whale evolution. It shows the moment in history when early whales had fully adapted to life in the ocean, becoming long serpentine predators that ruled ancient seas millions of years before modern whales swam the waters of our world. Over the years, many doubtful and poorly understood species were linked to Basilosaurus, but later research showed that most of them were either based on incomplete fossils or were simply mistakes. In science, when a name is given to a fossil, but there is not enough clear evidence to truly identify or describe it, that name can be called a nomen dubium, which means a doubtful name. Sometimes a fossil is so poorly described that it is called a nomen nudum, meaning it was named without a proper scientific explanation. One example is Zeuglodon wanklini, which was described in the year 1876 from a skull found at Wanklin's Barton Cliff in the United Kingdom. The problem was that this single fossil later disappeared. Without the specimen to study, scientists could not confirm what it truly was. Because of this, the name was declared invalid, and some researchers later connected it to another early whale called Zygohyza. Another questionable name was Zeuglodon vredensis, created in the 19th century from only a single tooth. There was no detailed description and no additional fossils. In the year 1936, the paleontologist Remington Kellogg declared it a nomen nudum because there simply was not enough information to support it as a real species. The same issue surrounded Zeuglodon pushi, which was said to come from Poland and was named in the year 1873 by Johann Friedrich von Brandt. It was based only on an incomplete vertebra. Because no one could even tell where exactly in the backbone that bone belonged, the species could not be properly identified and was later dismissed as invalid. Another confusing case involved Zeuglodon brachyspondylus, described by Johannes Peter Müller from several vertebrae that were linked to a strange fossil skeleton once displayed by Albert Koch, who had assembled it under the dramatic name Hydrarchos. Later research showed that this species was actually the same as Pontogeneus priscus, though even that name was eventually considered doubtful in the early 21st century. In the year 1997, a species called Basilosaurus drazindae was named from a single lower back vertebra. At first, scientists believed it lived in what is now Pakistan and the United Kingdom, and even thought it might be the earliest known example of Basilosaurus. However, in the year 2013, it was labelled a doubtful name. Then, in the year 2015, researchers reassigned it to another ancient whale called Eocetus, removing it from Basilosaurus altogether. Several other species once placed in the genus Zeuglodon, including Zeuglodon elliott-smithii, Zeuglodon sensitivus, and Zeuglodon zitterlii, were grouped together under a different ancient whale known as Sagacetus in the year 1992. There was also Zeuglodon paulsoni, named in the year 1873 from fossils found in what was then the Russian Empire, now Ukraine. It was later linked to Platyosphis, though debate continues over whether that genus itself is valid. Another species, Basilosaurus caucasicus, was described in the 1890s from fossils found in the Caucasus region. Later, scientists decided it actually belonged to a different toothed whale called Microzeuglodon caucasicum. In Australia, near the Murray River in South Australia, fossils were named Basilosaurus harwoodii. However, in the year 1911, the scientist Thomas Sargent Hall placed it in another genus called Metasqualodon, showing again how uncertain early classifications could be. In the early 20th century, confusion even extended to misidentifying body parts. In the year 1906, the German naturalist Othenio Abel believed that a fossil bone from Alabama, first described in the year 1900 as the hip bone of Basilosaurus by Frederick Augustus Lucas, was actually the shoulder bone of a giant flightless bird similar to Gastornis. He named it Alabamornis gigantea. 2 years later, Lucas corrected the mistake and confirmed that the fossil truly belonged to Basilosaurus. Despite all this confusion, Basilosaurus itself remains one of the largest animals known to have lived between the Great Extinction that wiped out the dinosaurs about 66 million years ago and about 15 million years ago, when modern whales began reaching enormous sizes. Two well-known species are Basilosaurus setoides, which measured between 17 and 20 meters long, and Basilosaurus isis, which reached between 15 and 18 meters in length. Earlier research in the year 1998 estimated their weight at a little over 5 to nearly 6.5 metric tons. However, a more recent study in the year 2025 suggested that a specimen of Basilosaurus setoides measuring just over 18 meters could have weighed as much as 15 metric tons, making it far heavier than previously believed. Basilosaurus stood out from other early whales because of its extremely long body. Its vertebrae in the chest, lower back, and front part of the tail were especially stretched out, giving it a snake-like appearance in the water. Unlike its relative Basilosaurus, Basilosaurus did not have certain vertically positioned bony projections on its vertebrae. It is considered the largest of the ancient whales known as Archaeocetes. The teeth of Basilosaurus were also impressive. In Basilosaurus isis, the dental formula shows that it had 3 incisors, 1 canine, 4 premolars, and 2 molars on each side of the upper jaw, and 3 incisors, 1 canine, 4 premolars, and 3 molars on each side of the lower jaw. The molars and some of the premolars had 2 roots and were tall and sharp, built for grasping and tearing prey. Its head was very different from that of modern toothed whales. It did not have room for a melon, the rounded fatty organ that living whales use to focus sound for echolocation. Its brain was also smaller compared to modern whales, and scientists believe it did not have the complex social behavior or advanced echolocation abilities seen in today's species. However, a study published in the year 2011 revealed something surprising. The skull of Basilosaurus was not perfectly symmetrical as once believed. Instead, it showed asymmetry similar to modern toothed whales. In living species, this uneven skull structure helps produce and detect high-frequency sounds. Even though Basilosaurus likely did not echolocate, this feature may have helped it better detect sounds underwater. It probably had a fatty sound receiving pad in its lower jaw that allowed it to sense the direction of noises in the ocean. Inside the skull, the middle and inner ear were protected by a dense bone called the tympanic bulla. Basilosaurus also had early versions of the special air sinus system found in whales today, including spaces in the pterygoid, peribulary, maxillary, and frontal regions of the skull. The bone surrounding the inner ear, known as the periotic bone, was partly separated from the skull, improving underwater hearing. The lower jaw contained a large canal bordered by a thin wall of bone, sometimes called the pan bone or acoustic window, which helped transmit sound. Compared to even earlier whales such as Remingtonocetids and Protocetids, Basilosaurids had more advanced ears. Air-filled sinuses helped isolate the ear from the rest of the skull, improving directional hearing underwater. Unlike modern whales, though, they still retained a relatively large external ear opening. While this outer ear may have worked on land or near the surface, it was probably not very useful when fully submerged. Through decades of discoveries, corrections, and debates, Basilosaurus has gone from being surrounded by confusion and misidentification to becoming one of the most fascinating and best understood giants of the ancient seas. At its full size, a single Basilosaurus isis could grow to about 16 meters in length, which is roughly the size of a large bus. Near the back of its long body, it carried tiny hind limbs that were only about 35 centimeters long. These small legs had fused ankle bones and just 3 toes. They were far too short and weak to support the animal's weight, and they were not even properly connected to the backbone at the hip region. Because of this, it is very unlikely that these limbs were used for walking or swimming. Instead, scientists believe they may have had a different purpose. Some researchers suggest that these small legs worked like claspers, helping guide the animal's long, snake-like body during mating. In this way, they may have played a role similar to the small pelvic spurs still seen today in some modern snakes, which are the last remains of their ancient limbs. In 2015, paleontologists discovered a complete skeleton of Basilosaurus, giving researchers a clearer picture of how this ancient whale was built. Earlier attempts to understand its backbone were based on incomplete fossils. In 1936, the scientist Kellogg studied 2 partial skeletons of Basilosaurus cetoides found in Alabama and estimated that the animal had about 58 vertebrae. However, more complete fossils uncovered in Egypt during the 1990s allowed scientists to make a more accurate reconstruction. By carefully studying 3 overlapping skeletons of Basilosaurus isis, researchers concluded that it likely had around 70 vertebrae in total. These included 7 neck vertebrae, 18 in the chest region, 20 in the lower back and sacral area, and 25 in the tail. Scientists believe that Basilosaurus cetoides probably had a very similar arrangement. The body of Basilosaurus was long and slender, shaped somewhat like an eel. This unusual shape was caused by the stretching of the central parts of the vertebrae from the chest down toward the front of the tail. When the animal was alive, these bones were filled with marrow and possibly fluid, which made them lighter and more buoyant. Because of this body design, Basilosaurus likely swam mostly near the surface of the sea. Unlike its smaller relative Dorodon, which probably dived and moved freely in 3 dimensions, Basilosaurus seems to have moved mainly in 2 directions, gliding forward and up or down near the water's surface. Its tail probably had a small fluke, but this fluke would have helped mostly with vertical motion rather than powerful forward thrust. The similar size of the vertebrae in the chest, lower back, sacral and tail regions suggests that Basilosaurus swam by moving its body in smooth, wave-like motions, much like an eel. These movements were likely mostly vertical, meaning the body flexed up and down. Paleontologist Philip D. Gingerick proposed that it might also have moved its body from side to side in a strange horizontal wave pattern at times, something not seen in modern whales. The vertebrae appear to have been hollow and possibly filled with fluid, which further supports the idea that this whale stayed near the surface rather than diving deep. Its backbone muscles were not especially strong, and its small hind limbs had thick, heavy bones. All of this suggests that Basilosaurus was not built for long-distance swimming, deep diving, or moving on land. Its teeth tell an important story about how it fed. The cheek teeth of Basilosaurus were complex in shape and fit together in a way that allowed it to chew its food. The heavy wear found on fossil teeth shows that it crushed and sliced its prey before swallowing it. By studying damage marks on the skulls of prehistoric whales and comparing them with fossils of Basilosaurus isis, scientists estimated that its bite force could reach at least 16,400 newtons and possibly more than 20,000 newtons. This is similar to the powerful bite range of modern crocodiles and alligators. Such strength made Basilosaurus a terrifying predator in its ancient seas. Evidence from stomach contents of Basilosaurus cetoides shows that it fed mainly on fish and large sharks. Meanwhile, bite marks found on the skulls of young Dorudon fossils match the teeth of Basilosaurus isis. This suggests that the two species may have had slightly different diets and hunting behaviors, similar to how different groups of modern killer whales specialize in different prey. The discovery of young Dorudon fossils at Wadi El-Hitan in Egypt, bearing clear bite marks on their skulls, suggests that Basilosaurus attacked the head to kill its prey quickly. After delivering a fatal bite, it likely tore the body apart, as shown by the scattered remains found at the site. These findings strongly support the idea that Basilosaurus was an active hunter, not a scavenger. It may even have targeted newborn and young Dorudon when mothers came into shallow waters to give birth. The stomach contents of one elderly male Basilosaurus isis even included remains of Dorudon, along with a fish called Pycnodus moccatamensis, proving that it hunted a variety of prey. Basilosaurus stood at the very top of its food chain. It lived during the warm tropical seas of the Eocene epoch, in shallow coastal waters rich with seagrasses such as Thalassodendron, Thalassia, also known as turtle grass, and Halodule. Fossils show that it preferred shallow marine areas, especially the middle to outer parts of the inland sea. In these waters, it shared its world with the dolphin-like Dorudon, other early whales like Cynthia cetus and Basiloterus, the primitive sea cow Protosiren, the early elephant Merytherium, the sea turtle Papygerus, and many types of sharks, including Galiocerdo alabamensis, Physogalius, Otodus, Squatina prima, Striatolamia, Carcharocles, Sokolovi, and Isurus precursor. In this rich and lively ecosystem, Basilosaurus ruled as a dominant predator, a long-bodied hunter cruising the warm, shallow seas millions of years before modern whales took over the oceans. The fossil record of Basilosaurus appears to come to an end around 35 to 33.9 million years ago. After that time, its bones disappear from the layers of rock, suggesting that this giant ancient whale no longer swam in Earth's oceans. Its extinction happened at the same time as the Great Eocene-Oligocene extinction event, which took place about 33.9 million years ago. This powerful global event wiped out nearly all of the other early whales known as archaeocetes, marking the close of an important chapter in whale evolution. Scientists have proposed several possible reasons for this massive die-off. Some believe that intense volcanic eruptions may have filled the atmosphere with ash and gases, changing temperatures and ocean chemistry. Others suggest that a meteor impact could have shaken the planet and disturbed life across land and sea. Another leading idea is that the world's climate suddenly cooled. If the oceans became colder, their circulation patterns may have shifted. Ocean currents act like giant moving highways of water, carrying heat, nutrients, and food across the globe. When those currents change, entire food chains can be affected. If prey animals became fewer because of disrupted currents or reduced nutrients rising from the deep sea, large predators like Basilosaurus would have struggled to survive. When Basilosaurus vanished, it left behind no direct descendants. The entire group of ancient whales known as archaeocetes eventually disappeared as well. Yet their extinction was not the end of whale history. In fact, it opened the door to something new. After this extinction event, the oceans developed stronger currents and deeper upwelling, where nutrient-rich waters from the depths rise toward the surface. These changes created fresh opportunities for evolution. From more advanced archaeocete ancestors emerged the first true modern whales, called Neocetes. These included the early toothed whales and baleen whales, which would later diversify into the many species we recognize today. When scientists study where Basilosaurus fits on the evolutionary tree, they place it within the family Basilosauridae. Within this family, two main subfamilies have been proposed. One is Basilosaurinae, which includes Basilosaurus itself. The other is Dorudontinae, which includes Dorudon. However, these groupings have not always been accepted without debate. In the past, some researchers argued that dividing Basilosauridae into these two subfamilies was not valid. There was even a time when fossils of Dorudon were thought to belong to young Basilosaurus individuals. Only later did scientists realize that Dorudon was a separate genus, not simply a juvenile form of its larger relative. Liopleurodon, whose name means smooth-sided tooth, was a powerful sea reptile that no longer exists today. It belonged to a group of short-necked plesiosaurs called pliosaurids and lived during the Middle to Late Jurassic period, from about 166 million to 155 million years ago. The main and most widely accepted species is Liopleurodon ferox, and many scientists believe this is probably the only true species in the genus. Another name, Liopleurodon pachydairus, has sometimes been suggested as a second species, but most researchers now think it is simply another name for Liopleurodon ferox because there are not enough clear differences to separate it. Fossils linked to Liopleurodon, including several partial skeletons, have mostly been found in Europe, with a single report coming from Mexico. Interestingly, the original specimen used to name Liopleurodon ferox was only a single tooth, and that tooth does not have many clear features that make it unique. Because of this, modern researchers have suggested choosing a new reference specimen, known as a neotype, to properly define and protect the name. Over the years, other supposed species were suggested, but these are now believed to belong to different pliosaur genera. Like all plesiosaurs, Liopleurodon had 4 strong flippers that it used to swim through the sea with great power and control. It had a short tail, a massive head, and a short, thick neck, which was typical of pliosaurids. In one famous television series, Walking with Dinosaurs, released in 1999 by the BBC, Liopleurodon was shown as a gigantic monster reaching about 25 meters in length. This dramatic portrayal captured the imagination of millions of viewers, but it greatly exaggerated the animal's true size. Fossil evidence suggests that most individuals were between 4 and 8 meters long, although some scientists think the very largest might have reached around 10 meters. Even at that more realistic size, Liopleurodon would still have been one of the top predators in the Jurassic oceans. Studies of its skull and teeth show that it likely hunted by ambush, using sudden bursts of speed to catch fish, squid-like cephalopods, and even other marine reptiles. Long before the name Liopleurodon was officially created, scientists had already discovered fossils that probably belonged to this animal. In the year 1838, the German paleontologist Hermann von Meyer gave the name Ichthyosaurus meriani to a large fossil tooth found in rocks in Switzerland that likely dated back to the Colovian age. However, that tooth did not have enough special features to clearly identify what creature it came from. Decades later, in 1960, the researcher Lambert Beverly Tarlow suggested that it might actually belong to Liopleurodon. Much more recently, in 2022, Daniel Madzia and his colleagues studied the tooth again. They concluded that while it may have come from Liopleurodon or a similar animal, there was not enough solid evidence to be certain, so they classified the name Ichthyosaurus as doubtful. In 1841, Hermann von Meyer named another fossil Thaumatosaurus Olithicus, based on incomplete remains from Germany that included parts of teeth, pieces of skull, vertebrae, and ribs. Unfortunately, these fossils also lacked clear features that would allow scientists to confidently identify them. Later, in 1852, Johann Andreas Wagner described a large plesiosaur tooth from Bavaria and called it Pliosaurus giganteus. However, this name had already been used earlier, in 1824, by William Conybeare for a different species, Plesiosaurus giganteus. Because scientific rules do not allow the same name to be used twice for different animals, Wagner's name was invalid. Then, in 1860, Hermann Trautschuld used the same name, Plesiosaurus giganteus, for a small tooth found in Russia. By that time, the name had already been used twice, so his version was also invalid. Today, that Russian tooth is thought to likely belong to Liopleurodon. The official name Liopleurodon was created in 1873 by the French paleontologist Henri-Émile Sauvage. He named 3 species within this new genus, each based on a single tooth. The main species, Liopleurodon ferox, was based on a tooth found near Boulogne-sur-Mer in France. The tooth crown measured about 7.5 centimeters long and came from rocks dating to the Calovian stage of the Middle Jurassic. The species name ferox comes from Latin and means fierce, a reference to the large, sharp teeth that suggested a powerful predator. The genus name comes from ancient Greek words meaning smooth, side, and tooth, describing the smoother sides of its teeth compared to some related animals. In 1880, Sauvage decided that Liopleurodon was so similar to another marine reptile called Polyptychodon that he combined them under one name. A few years later, in 1888, the British paleontologist Richard Lydekker studied teeth from the Oxford clay of England and concluded that they looked very similar to those of Pliosaurus, so he placed them in that genus instead. Around the same time, in 1869, Harry Govier Seeley had named Pliosaurus pachydiurus based on a series of neck vertebrae from England. The name pachydiurus means thick neck, referring to the strong vertebrae. Later scientists suggested that this material might actually belong to Liopleurodon ferox rather than a separate species. In 1883, Walerian Kiprianov named another species, Thaumatosaurus moskensis, based on fossils from Russia, but this too was later considered probably just another example of the same fierce predator. Over time, as more fossils were studied and compared, scientists slowly untangled this confusing history of names and misidentifications. Today, Liopleurodon stands as one of the most impressive hunters of the Jurassic seas, not the impossible 25-meter monster once shown on television, but still a massive, powerful marine reptile whose smooth-sided teeth and crushing bite made it one of the dominant predators of its time. In the year 1905, the British paleontologist John Frederick Blake carefully described 2 fossil teeth that had been found in Rushden, England. These teeth looked very much like the teeth of Liopleurodon ferox, yet they came from rock layers that were older than the famous fossils discovered around Peterborough. Blake noticed something important. The teeth did not match those of Pliosaurus, and the bones known at the time were also different from those of Polyptychodon. Because the fossils did not clearly belong to either group, Blake suggested that the name Liopleurodon should be brought back into use as its own proper genus. A few years later, in 1912, the Russian scientist Nikolai Bogolyubov also treated Liopleurodon and Pliosaurus as separate genera, even though he had earlier thought Liopleurodon might only be a smaller subdivision within Pliosaurus. When Richard Lydekker first visited the famous fossil collection of Alfred Leeds, known as the Leeds Collection, the only remains of Liopleurodon, there were teeth. But over time, Alfred Leeds and his brother Charles Edward Leeds discovered many more fossils. They found skulls and large parts of the skeleton behind the head, giving scientists a far better understanding of the animal's full body. These important fossils were later studied in detail by Charles William Andrews. He described the marine reptile fossils from the Leeds collection in two large books, published in 1910 and 1913. In the second book, he discussed the Liopleurodon specimens, although he still believed they actually belonged to Pliosaurus. In 1913, the German scientist Hermann Linde also described fossils of Liopleurodon ferox. One of these fossils was a badly preserved partial skeleton found in the Oxford clay at Fletton, England. This skeleton, now kept at the University of Tübingen in Germany, had been mounted for display, and the missing parts were rebuilt using material from other Liopleurodon fossils. Like Andrews, Linde believed the animal should be called Pliosaurus ferox instead of Liopleurodon ferox. He also described several skulls from Fletton that were kept in Tübingen and in Stuttgart, assigning them to Pliosaurus grandis. In addition, he placed a nearly complete paddle under Pliosaurus as well. Later studies showed that all these fossils likely belonged to Liopleurodon, although scientists do not agree equally strongly about each specimen. Sadly, one of the skulls kept in Stuttgart was destroyed during the Second World War. In 1934, Friedrich von Huene described another partial skeleton from Swabia in Germany and also used the name Pliosaurus ferox. A few years later, in 1938, Alexandre Bigot followed the same naming choice when he studied teeth found in Calvados in northern France. A major turning point came in 1960 when Lambert Beverly Halstead, who had earlier been known as Tarlo, published a detailed review of large marine reptiles from the Upper Jurassic. He argued strongly that Liopleurodon was truly different from Pliosaurus. He pointed out major differences in the lower jaws of the two animals. Besides Liopleurodon ferox, he also moved another species, Pliosaurus pachydairus, into Liopleurodon and renamed it Liopleurodon pachydairus. He believed the differences in teeth and neck bones were important enough to separate them. However, he did not accept Liopleurodon grossouvre as valid, though he cautiously kept the name for certain teeth found in the Kellerways Formation. In 1971, Halstead published another study, this time focusing on Pliosaurus rossicus. After examining it more closely, he decided it was a valid species but placed it inside Liopleurodon because of its short lower jaw joint. He also moved Pliosaurus macromerus, which he had once placed in its own genus called Stretosaurus, into Liopleurodon. Later, scientists discovered that a bone he had thought was a shoulder blade was actually part of the hip, showing how easily fossils can be misunderstood. In 1992, David Martial described a fragmentary fossil from a young individual identified as possibly belonging to Liopleurodon. This specimen contained at least 7 gastroliths, or stomach stones, showing that the animal likely swallowed stones to help digest food. Soft tissues were also present, but they were too poorly preserved to study in detail. The following year, Nathalie Bardet and her colleagues identified 2 teeth from Villers-sur-Mer in Normandy, France, as belonging to Liopleurodon ferox. In 2001, Leslie F. Noé argued in his doctoral research that Liopleurodon pachydairus could not be clearly distinguished from Liopleurodon ferox. He suggested that Liopleurodon ferox might be the only truly valid species. The teeth of the mounted skeleton in Tübingen, once assigned to Liopleurodon pachydairus, actually showed features typical of Liopleurodon ferox. Noé also argued that differences in neck bones were not reliable for separating species, and that variations in tooth shape could simply reflect differences between individuals rather than separate species. He removed both Liopleurodon macromerus and Liopleurodon rossicus from the genus. One was tentatively returned to Pliosaurus, and the other might require a completely new genus. Most Liopleurodon fossils have been found in England and France, but similar fossils dating from the Colovian to the Kimmeridgian ages have also been discovered in Germany. In 2012, Espen Knudsen reassigned both Macromerus and Rossicus back to Pliosaurus. In 2013, Roger Benson and his team agreed with this decision, although they considered Pliosaurus macromerus doubtful because no official replacement specimen had been chosen. They also suggested that Liopleurodon may have existed only during the Middle Jurassic period. In 2015, Jair Israel Barrientos Lara and his colleagues described two large marine reptile fossils found near Tlaxiaco in Oaxaca, Mexico. These fossils came from Kimmeridgian rock layers, and part of a snout appeared to belong to Liopleurodon. However, the remains were too incomplete to identify the exact species. Later, in 2018, Davide Foffa and his team suggested that Liopleurodon grossouvre might actually represent a separate genus, rather than being the same as other species. In 2022, Daniel Madzia and colleagues pointed out a serious problem. Liopleurodon had originally been named based on just a single tooth, and that tooth might not be distinctive enough. They suggested that a new, more complete reference specimen might be needed to keep the name stable. They also emphasized that more research is required to confirm whether the differences between Liopleurodon ferox and Liopleurodon pachydairus truly reflect individual variation. Most recently, in 2024, Peggy Vincent and her co-authors described a partial skeleton discovered decades earlier, in 1979, in an abandoned quarry at Saint-Laurent in France. This fossil, informally known as the Thouarsais specimen, comes from Colovian rock layers, the same age as the original tooth that gave Liopleurodon its name. Measuring a little over 3 meters in preserved length, it is one of the most complete Liopleurodon skeletons known from France and provides valuable new insight into the body structure of this powerful Jurassic sea predator. Plesiosaurs are usually described in two main body types. One type had a small head and a very long neck. Scientists call this form the plesiosauromorph shape. The other type had a large head and a short, thick neck, known as the plesiosauromorph shape. Liopleurodon belonged to this second group. Instead of a long, swan-like neck, it had a huge skull built for power. Like all plesiosaurs, it had a short tail, a broad and heavy body, and two pairs of large, strong flippers that helped it move through the water. When the French scientist Henri-Émile Sauvage first described Liopleurodon in the year 1873, he examined a single tooth from the species Liopleurodon ferox. Even from that one tooth, he believed the animal must have reached truly gigantic size. Decades later, Liopleurodon became world famous in the year 1999 when it appeared in the television series Walking with Dinosaurs produced by the BBC. In that program, it was shown as a massive ocean super predator about 25 meters long and weighing around 150 tons. Viewers saw it as a sea monster larger than most whales alive today. This enormous size was based on a single vertebra found near the English city of Peterborough. A consultant to the series used that bone to estimate a much larger body. At the time, the idea seemed reasonable. However, later research showed that this size estimate was far too extreme. Even the same consultant later agreed that the reconstruction had likely been exaggerated. Fossils of very large pliosaurs are often incomplete, and broken pieces can easily give the wrong impression. Some scientists even questioned whether the Peterborough vertebra belonged to a pliosaur at all. In the year 2019, a detailed study concluded that the bone actually came from a long-necked plant-eating dinosaur known as a sauropod, not from Liopleurodon. For many years, scientists tried to estimate the full body length of pliosaurs by comparing skull size to total length. The paleontologist Leslie B. Tarlow suggested that the skull usually measured about 1/7 of the animal's total body length. Using this method, he believed the largest known Liopleurodon ferox specimen would have been slightly more than 10 meters long. He also suggested that most individuals were probably between 5 and 7 meters in length. However, later discoveries changed this view. Fossils of other pliosaurs, including Kronosaurus, and a more complete skeleton of Liopleurodon, showed that the skull was closer to 1/5 of the total body length, not 1/7. This meant earlier calculations needed correction. One large skull specimen suggested a total body length of a little over 6 meters. Smaller individuals measuring between about 4 and 5 meters may have weighed around 1 to almost 2 tons. More recent research published in the year 2024 estimated that the largest known Liopleurodon specimen could have reached around 8 meters long with a body mass close to 8 tons. Some researchers still believe certain individuals may have grown beyond 10 meters, but most evidence today supports a size that, while impressive, was far smaller than the giant shown on television. Liopleurodon belonged to a group of short-necked pliosaurs known as Thalassophonea, within the family Pliosauridae. These powerful marine reptiles lived from the Middle Jurassic into the early part of the Late Cretaceous period and have been discovered all over the world. Liopleurodon itself is considered one of the more early members of this powerful branch during the Middle Jurassic. Compared to later relatives from the Upper Jurassic, it had fewer tooth sockets, a somewhat smaller skull, and a smaller overall body. Its body design reveals much about how it lived. With 4 strong paddle-shaped flippers, Liopleurodon was clearly built for swimming. All plesiosaurs used this 4-flipper system. Studies using swimming robots have shown that this style of movement may not have been the most energy-efficient way to travel long distances, but it allowed for sudden bursts of speed. That quick acceleration would have been extremely useful for a predator that relied on surprise. Instead of chasing prey over long distances, Liopleurodon may have attacked suddenly from below or from behind. Studies of its skull also suggest that it could sense smells in the water using its nostrils, possibly helping it track prey. Evidence of its diet comes from a fragmentary fossil that may have belonged to a young individual. Inside its stomach area, scientists found many small hooks from squid-like animals, along with fish bones and a single reptile tooth. These hooklets came from soft-bodied cephalopods similar to modern squids. The exact diet of Liopleurodon is still debated. One idea is that it fed mainly on squid, since they were abundant. However, squids are fast swimmers, and plesiosaurs were probably slower in steady swimming, which makes this explanation less convincing unless Liopleurodon relied on ambush attacks. Another possibility is that it was an opportunistic feeder that ate many different kinds of prey. The squid hooks may simply be the hard parts that survived the strong stomach acids, while other bones dissolved completely. Interestingly, scientists did not find small ear stones known as otoliths, which are common in fish and often survive digestion in modern whales. This suggests that fish might not have been a major part of its diet. A third idea is that Liopleurodon may have eaten animals that themselves fed on cephalopods, meaning the squid hooks were actually leftovers from the stomach contents of its prey. However, there is no solid proof for this idea. The same fossil also contained at least 7 small stones called gastroliths. These stones are sometimes used by animals to help grind food in the stomach. In this case, however, the squid hooks were very well preserved, which suggests the stones were not used for grinding. It is possible the animals swallowed the stones by accident, or that they represent tough mineral fragments that survived digestion. Altogether, Liopleurodon was not the impossible sea monster once imagined on television, but it was still a powerful and dangerous marine predator. With its massive head, strong jaws, sharp teeth, and sudden bursts of speed, it ruled parts of the Jurassic seas with strength and efficiency, proving that even without exaggerated size, it was one of the most formidable hunters of its time. Kronosaurus was a massive marine reptile that lived during the early Cretaceous period, roughly from the Aptian to the Albian stages, in the waters that now make up Australia. It belonged to a group of short-necked pliosaurs, fierce ocean predators with enormous heads and powerful jaws. The first fossil linked to this giant was received by the Queensland Museum in 1899. It consisted only of a partially preserved front section of the lower jaw, known as the mandibular symphysis. At first, the museum director, Charles de Vis, believed it came from an ichthyosaur, a different type of marine reptile. It was only in 1924 that Albert Heber Longman carefully examined the fossil and formally recognized it as a pliosaur. He gave it the scientific name Kronosaurus queenslandicus, which remains the only officially recognized species today. The genus name, meaning lizard of Kronos, refers to its enormous size and likely terrifying presence, reminiscent of the Greek titan Kronos, famous in mythology for devouring his own children. The species name honors Queensland, the Australian state where the fossil was probably found. In the early 1930s, the Harvard Museum of Comparative Zoology sent a well-organized expedition to Australia. They recovered 2 additional specimens historically linked to Kronosaurus, including a nearly complete skeleton that was later heavily restored in plaster. Over the years, other fossils have been found, including 2 large partial skeletons. Because the original fossil lacks enough distinctive features to clearly separate Kronosaurus from other pliosaurs, scientists now suggest that these 2 skeletons could serve as neotypes for future studies. While 2 other species were once proposed, they are no longer considered valid and likely belong to different genera. Kronosaurus is among the largest pliosaurs ever discovered. Early estimates based on the Harvard skeleton suggested it could grow up to 13 meters or 43 feet in length. However, that skeleton was reconstructed with too many vertebrae, and modern estimates from the early 2000s now suggest a more realistic length between 9 meters or 30 feet and just over 10 meters or 33 feet. Like all plesiosaurs, Kronosaurus had 4 strong paddle-like limbs and a short tail. Unlike the long-necked varieties, its head was huge and its neck short. The largest skulls found are even bigger than those of the largest known land predators, the theropod dinosaurs. The front of the skull extended into a long snout, and the lower jaw, where the 2 halves meet at the front, contained up to 6 pairs of sharp, cone-shaped teeth. These teeth were perfectly designed to seize and crush large prey, with the front teeth being larger than those at the back. Its limbs had evolved into powerful flippers, with the hind pair larger than the front, giving the largest Kronosaurus individuals a flipper span of more than 5 meters, or 16 feet. Recent studies place Kronosaurus within a subfamily called Brachiosaurinae, a group of pliosaurs that thrived at various times during the Cretaceous. Fossils show that Kronosaurus lived in the Eromanga Sea, a vast inland ocean that once covered much of Australia during the early Cretaceous. This sea was cold, with waters near freezing. In this environment, Kronosaurus was likely the top predator. Fossil evidence shows it hunted sea turtles and even other plesiosaurs. Scientists estimate its bite force could reach between 15,000 and 27,000 newtons, or 3,370 to 6,070 pounds of force. Interestingly, the skull of a juvenile fossil shows marks that suggest it was attacked by an adult, hinting at aggressive behavior within the species, or possibly even cannibalism. Kronosaurus would have also faced competition from other large predators, as some specimens show bite marks from sharks similar to Cretoxyrhina. The story of Kronosaurus begins with a partial fossil sent to the Queensland Museum in 1899 on behalf of Andrew Crombie. Charles de Vis, then the museum director, received it, though the exact discovery site is unknown. It was likely near Hughenden in Queensland, where Crombie lived. De Vis initially thought the fossil belonged to an ichthyosaur, probably Ichthyosaurus australis, now considered part of the genus Platypterygius. The unique shape of the teeth, however, soon convinced him that it represented something entirely different. The The fossil was officially described by his successor, Albert Haber Longman, in a 1924 publication in the Queensland Museum Journal. Longman named it Kronosaurus queenslandicus, combining the Greek titan Kronos and the Greek word for lizard, sauros, to convey the image of a giant, fearsome predator. The species name references Queensland, the state where the fossil likely originated. In August of 1929, approximately 15 partial fossils were discovered nearly 3 kilometers and 200 meters south of the town of Hughenden. All of these fossils were catalogued under the number QMF 2137 and were identified as originating from the Toolbuck Formation, which dates back to the Albian stage of the early Cretaceous period. It is very likely that the holotype, the specimen used to formally describe the species, was also discovered in this same area. Most of the fossils recovered at this time were very incomplete, with only 2 pieces that could be clearly described. These were the upper portions of the limb bones, known as propodials. These bones were studied in greater detail the following year, with Longman conducting another analysis as well. In 1932, in an effort to make the fossils more visually appealing and understandable to the public, Longman published one of the earliest known reconstructions of Kronosaurus. The illustration, completed in 1931 by an artist named Wilfred Morden, relied heavily on comparisons with the anatomical features of Peliniustes to fill in the missing parts of the creature. Then, in April and May of 1935, J. Edgar Young, working for the Queensland Museum, collected several additional fossils from the Toolbuck Formation, this time from the Telemon Station, located about 30 kilometers west of Hughenden. Among these finds were new remains attributed to Kronosaurus, including the first relatively complete portions of the skull identified for the genus. In an article published in October of 1935, Longman suggested that the fossils represented at least 2 or 3 individual animals, noting that the fossils were not fully prepared at the time and offering only a preliminary description. The most significant of these fossils, catalogued as QMF 2446, included a partial middle section of the skull. This specimen preserved the occipital condyle, the back of the brain case, the external nostrils, and the eye sockets, providing crucial information about the animal's anatomy. Meanwhile, in 1931, the Museum of Comparative Zoology in the United States organized an expedition to Australia with the dual purpose of collecting both living and extinct specimens, particularly focusing on marsupial mammals. The museum aimed to expand its collection of Australian fauna, which had previously been limited. This mission became known as the Harvard Australian Expedition and included a team of 6 men: P. Jackson Darlington Jr., a specialist in beetles, zoologist Glover Murrill Allen and his student Ralph Nicholson Ellis, chief physician Ira M. Dixon, paleontologist William E. Sheville, and the expedition leader, entomologist William Morton Wheeler. By 1932, Sheville had become the official leader of the expedition. He undertook long journeys across remote areas, enlisting local help whenever possible. Although the Queensland Museum was invited to participate, the plan was never approved due to lack of funding or interest from the state government. Longman, who had previously described the first Kronosaurus fossils, assisted the expedition regardless, storing specimens, securing collecting permits, and maintaining correspondence with Sheville. Sheville focused his efforts on the Rolling Downs Geological Group, north of the town of Richmond, where he collected 2 large pliosaur specimens from the Doncaster member of the Wallumbilla Formation, dating back roughly 112 million years. The first of these specimens, catalogued as MCZ 1284, was found on a property called Grampian Valley. It included a well-preserved piece of the front part of the snout, closely connected to the entire lower jaw, along with several other fragmentary bones. The story of the second specimen, catalogued as MCZ 1285, is more detailed in historical accounts. This specimen had actually been discovered before the Harvard expedition even began by a rancher named Ralph William Haslam Thomas at a location called Army Downs. Thomas had long been aware that something strange was emerging from the ground in a small horse enclosure. These objects turned out to be a row of vertebrae encased in rock nodules. Recognizing their significance, Thomas informed members of the Harvard expedition, particularly Sheville. To extract the enormous fossil, which weighed approximately 4.5 metric tons, Sheville hired a British migrant trained in explosives nicknamed the Maniac by locals. The fossil, still embedded in its massive rock matrix, was carefully removed and shipped to the United States in 86 crates, totaling 6 metric tons. According to the export permit, the shipment left aboard the SS Canadian Constructor around the 1st of December, 1932. Once at Harvard, the fossils, which represented about 60% of the complete skeleton, took several years to carefully remove from the limestone due to limited funds, manpower, and space at the museum. In 1934, Sheville requested that Longman send a cast of the holotype's mandibular symphysis for comparison with the new specimen. Longman's assistant, Tom Marshall, fulfilled the request. Comparisons confirmed that the characteristics of the holotype, QMF 1609, matched those of the Harvard specimen, MCZ 1285. Longman expressed in letters that he would have enjoyed seeing the specimen during its preparation in the late 1930s, though he never travelled outside Australia. The first scientific description of the skull was completed by Theodore E. White in 1935, and 4 years later, in 1939, the specimen was finally exhibited at the museum. For more than 15 years, the rest of the skeleton lay forgotten in the basement of the museum, hidden from view and untouched. This long period of neglect ended when the fossils captured the attention of Godfrey Lowell Cabot, a wealthy industrialist, generous philanthropist, and founder of the Cabot Corporation in Boston. Cabot's family had a history of claiming to see enormous sea serpents in the coastal waters near his hometown. Curious about these mysterious reports, he asked the museum director, Alfred Sherwood Romer, about the existence of sea serpents. In response, Romer remembered the skeleton stored in the museum's basement and told Cabot about it. Cabot then asked how much it would cost to have the skeleton restored. Romer, perhaps joking, replied that it would be about $10,000. Cabot, however, was serious, because a check for exactly that amount arrived at the museum shortly afterward. Romer's own research interests focused primarily on non-mammalian synapsids, so he may not have seen the skeleton as a subject worthy of detailed scientific study. Nevertheless, under his supervision, Arnold Lewis and James A. Jensen worked carefully for 2 full years on the preparation of the fossil using chisels and acid, eventually costing slightly more than the original $10,000. The fully restored Harvard skeleton was exhibited for the first time on the 10th of June, 1958, followed by a detailed scientific description published the next year in the museum's journal by Romer and Lewis. When the completion of the specimen was reported in the Australian press, the original describer of the genus, Longman, was not mentioned. In protest, professor and geologist Walter Hayward Bryan sent a telegraph to journalists, warning that it would be unfortunate if such an important discovery ignored Longman and his interpretation of the initially fragmentary fossil material. Remarkably, at the age of 93, Thomas, the man who first discovered the specimen, was able to see the fully mounted skeleton of what he considered his dinosaur. He also reunited with the leader of the museum's earlier expedition, both surprised to find the other still alive after believing the other had long since passed away. As paleontology advanced, the restoration overseen by Romer began to be questioned. Because many of the bones were incomplete, Romer had instructed Lewis and Jensen to fill missing sections with plaster where he thought it necessary. While this allowed the skeleton to appear complete for display, it made it much harder for later scientists to study the actual fossil material. so much so that some paleontologists jokingly nicknamed the specimen Plasterosaurus. Furthermore, the skeleton was reconstructed with incorrect proportions. Australian paleontologist Colin McHenry noted that the spine had 8 extra vertebrae added, and the skull had been shaped with a bulbous sagittal crest that it would not have had in life. In his 1999 thesis revising the genus Kronosaurus, McHenry called the Harvard skeleton a rather disappointing restoration of what must have been an excellent fossil specimen. Many researchers have since expressed a desire to study the real bones using modern techniques such as computerized tomography scanning. The original holotype specimen of Kronosaurus queenslandicus, catalogued as QMF 1609, is incomplete and lacks unique features to clearly distinguish it from other pliosaurs. Because of this, the validity of the genus has long been questioned. As early as 1962, Samuel Paul Wells considered Kronosaurus a nomen varnum, meaning an invalid name, and suggested that a neotype from Harvard could help preserve the genus. Beginning in 1979, a number of large pliosaur fossils were discovered across various Australian locations, mostly in the Toolbuck Formation, where the first Kronosaurus fossils had been found. Additional specimens were discovered in the Doncaster member of the Wallumbilla Formation, 3 more in the Alaru Formation, and 2 fragmentary specimens in the Bulldog Shale. In his 1999 thesis, McHenry described many of these fossils in detail, proposing that 2 partial skeletons from the Toolbuck Formation, catalogued as QMF 10113 and QMF 18827, could serve as candidate neotypes because they appeared to match the original holotype. However, no formal request was submitted to the International Commission on Zoological Nomenclature. In 2022, researchers Leslie Francis Noé and Marcela Gomez Perez reviewed most of the specimens historically assigned to Kronosaurus. They concluded that Kronosaurus should only refer to the holotype and treated it as a nomen dubium, a name of doubtful validity. The other fossils were provisionally assigned to a new genus, Ichthyosaurus longmani, in honor of Longman, the paleontologist who first named the genus. The Harvard skeleton, catalogued as MCZ 1285, was also designated as a holotype for this new genus. Because the original specimen of Kronosaurus used to define the species is incomplete and cannot provide clear diagnostic features, most of what scientists know about its anatomy comes from more complete fossils that were later assigned to this genus. Much of the detailed description comes from John McHenry's thesis, published in 2009, though some additional specimens have been described in other scientific works. Plesiosaurs, the group to which Kronosaurus belongs, are typically divided into 2 main body types, one with small heads and long necks, called plesiosauromorphs, and another with large heads and short necks, called pleosauromorphs. Kronosaurus falls into this second, large-headed, short-necked category. Like all plesiosaurs, it had a short tail, a massive, robust body, and 2 pairs of large, powerful flippers, perfectly adapted for swimming through ancient oceans. Kronosaurus is recognized as one of the largest pliosaurs ever discovered, though its exact size has been the subject of debate for many years. As early as 1930, the researcher Longman, while describing parts of its limbs, suggested that Kronosaurus may have surpassed the already enormous Megalnusaurus, a pliosaur from North America that lived during the late Jurassic period. After the Harvard expedition collected fossils attributed to this genus, the maximum size of Kronosaurus was often estimated at 12.8 meters long, which is about 42 feet, based on the specimen known as MCZ 1285. For many years, Kronosaurus held the title of the largest known marine reptile until 1995, when Thiergarten Lingham Solier proposed that the late Cretaceous aquatic reptile Mosasaurus hoffmanii could reach around 18 meters or 59 feet in length. Later studies revised this size downward to roughly 11 meters, or 36 feet. Today, the record for the largest known marine reptile belongs to the late Triassic Ichthyosaur Ichthyotitan, which may have reached about 25 meters, or 82 feet, long. Because the Harvard skeleton was reconstructed incorrectly, McHenry suggested a smaller size for MCZ 1285, estimating it between 9 and 10.5 meters, or 30 to 34 feet, in length, with a weight of around 11 long tons, roughly 12 short tons. These measurements are now considered the maximum likely size for Kronosaurus as a whole. Even before McHenry's work, paleontologist Benjamin P. Keir and marine biologist Richard Ellis published their own estimates in 2003, suggesting sizes ranging from 9 meters, or 30 feet, according to Keir, up to 10.6 meters, or 35 feet, according to Ellis. More recently, in 2024, Ruige Jacovan Zhao revised the length of MCZ 1285 to 10.3 meters, or 34 feet. Other fossils have allowed scientists to estimate body sizes even when remains are incomplete. The holotype specimen, QMF 1609, although very fragmentary, would have measured about 5.9 meters or 19 feet in length, weighing nearly 2 long tons, roughly 2.1 short tons. A proposed neotype specimen, QMF 18827, would have been about 8.9 meters or 29 feet long, weighing approximately 6.7 long tons or 7.4 short tons. The most complete known specimen, QMF 10113, was slightly smaller at 8.6 meters or 28 feet in length, with a weight of 5.7 long tons or 6.3 short tons. The largest Kronosaurus specimens found in the Toolbuck Formation, QMF 2446 and QMF 2454, would have reached nearly the size of the Harvard skeleton, measuring between 10.2 and 10.5 meters, or 33 to 34 feet, in length, with estimated body weights ranging from 9.9 to 15.5 tons, or roughly 10 to 17 short tons. Because the holotype of Kronosaurus queenslandicus, QMF 1609, consists of only a small portion of the lower jaw, very little can be said about it. However, more complete skulls assigned to this species display several unique features. Skull sizes vary among specimens. The original holotype, although fragmentary, comes from a skull that would have measured about 1.31 meters or 4.3 feet long. Candidate neotype specimens, QMF 10113 and QMF 18827, have skull lengths reaching 1.87 to 1.98 meters or 6.1 to 6.5 feet. The skull of the Harvard skeleton is estimated at 2.85 meters or 9.4 feet long. These measurements make the skulls of these specimens larger than any known theropod dinosaur skull. The snout and jaw are long and narrow, with the rostrum gently arched and extended, featuring a distinct crest along the middle and top. The eye sockets face slightly backward and are positioned on the sides of the front half of the skull. The openings at the back of the skull, called temporal fossae, are very large, but the skull does not have a front opening in the roof between the pterygoid bones. Kronosaurus also has several distinctive traits in its skull. The premaxillar or front upper jawbone contains 4 canine-like teeth instead of 5 or more. The frontal bones, which border the eye sockets, do not touch the edge of the eyes because the postfrontal and prefrontal bones connect there. These frontal bones also do not meet the middle of the skull roof because of connections between the parietal bones and the back parts of the premaxilla. The prefrontals are large, contacting the front middle portion of the eye sockets and the back edge of the nostrils. Lacrimal bones, which form the lower front edge of the eye sockets, are present in young specimens but often fuse in adults. The median dorsal crest, a ridge on the top of the skull, is formed by fused premaxillae and nasal bones in adults. The hyoid bones, which support the tongue, are strong and robust. The lower jaw of Kronosaurus is elongated and spoon-shaped, similar to its close relatives Brachioceneus and Megacephalosaurus, containing up to 6 pairs of teeth. Each dentary, the main tooth-bearing bone, can hold up to 26 teeth. The jaw joint socket, called the mandibular glenoid, is kidney-shaped and angled upward and inward. Kronosaurus teeth are unique. They are conical, somewhat ridged, and lack sharp edges called carinae. Its teeth vary in shape, with large canine-like teeth at the front for seizing prey, and smaller, stouter, backward curving teeth at the back for slicing and gripping. The skeleton historically attributed to Kronosaurus at Harvard was studied in 1959 by Romer and Lewis, who focused on its postcranial anatomy, meaning all of the skeleton except the skull. However, because much of this skeleton had been heavily restored using plaster, it is now very difficult to tell which parts are real fossil material and which are reconstructions. At present, the specimen is temporarily referred to as Ichthyosaurus, and researchers hope that future CT scans may clarify whether it truly belongs to Kronosaurus. Many other Kronosaurus specimens do preserve postcranial bones. The most complete of these, catalogued as QMF10113, retains a large portion of the skeleton beyond the skull, offering crucial information that could provide a much deeper understanding of the species. Scientists plan to describe this specimen in greater detail in upcoming studies. Certain aspects of Kronosaurus's postcranial anatomy have already been discussed in McHenry's thesis and other publications. From studying various specimens, McHenry estimated that Kronosaurus had at least 35 presacral vertebrae, the vertebrae before the hip, including 13 cervical vertebrae in the neck and 5 pectoral vertebrae near the shoulders. Unlike its relative Pliosaurus, the vertebral bodies in the neck were wider than those in the back. The front dorsal vertebrae were taller than they were wide, and certain structures called zygapophyses, which normally connect vertebrae, were absent in both the front dorsal and tail vertebrae. In the thoracic region, the ribs were very robust, supported by equally strong transverse processes, and the ribs were single-headed, attaching at only one point on the vertebrae. Although no articulated tail of Kronosaurus has been found, the ends of the tail vertebrae likely supported a small caudal fin, similar to other plesiosaurs. Both the coracoid and the pubis bones were elongated from front to back. Interestingly, the hind limbs of Kronosaurus were longer than the forelimbs, and the femur was both longer and stronger than the humerus. This suggests that the largest Kronosaurus individuals could have had rear flippers forming a wingspan of over 5 meters or approximately 16 feet. When Kronosaurus was first discovered, De Vries thought the holotype specimen belonged to an ichthyosaur. However, when Longman formally described the species in 1924, he assigned it to the family Pliosauridae based on multiple anatomical features, a classification widely accepted throughout the 20th and 21st centuries. Alternative classifications were occasionally proposed. For example, in 1962, Wells suggested Kronosaurus might belong to the family Dolichorhynchopidae, but this family is now considered an unnatural grouping and invalid. The precise evolutionary position of Kronosaurus within Pliosauridae has been debated. In 1992, Hampe suggested grouping Kronosaurus with its close relative Brachioceneus into a family called Brachiochenidae. Kenneth Carpenter agreed in 1996, noting some important skull differences between the two genera. The family Brachiochenidae was originally established in 1925 by Samuel Wendell Williston to include only Brachioceneus. In 2001, F. Robin O'Keefe revised Pliosauridae and placed Kronosaurus as a basal member, only distantly related to Brachioceneus. Later, in 2008, several studies proposed alternative classifications. Patrick S. Druckenmiller and Anthony P. Russell considered Kronosaurus a more derived pliosaurid, while Hilary F. Ketchum still classified it as a sister taxon to Brachauchenius. Adam S. Smith and Gareth J. Dyke reclassified both genera within Brachauchenidae, but considered the family a sister group to Plesiosauridae. McHenry suggested that if Ketchum's classification proves valid, Brachauchenidae should be treated as a subfamily of Plesiosauridae and renamed Brachaucheninae, although he continues to use the original name in his detailed thesis on Kronosaurus. In 2013, Roger B. S. Benson and Patrick S. Druckenmiller established a new clade within Plesiosauridae called Thalassophonea. This group included the classic short-necked plesiosaurids, while excluding earlier, long-necked and more slender forms. They reassigned Brachauchenidae as a subfamily, Brachaucheninae, and included many Cretaceous plesiosaurids like Kronosaurus. Within this subfamily, Kronosaurus appears to be one of the most advanced members, often grouped with Brachauchenius, and more recently with Megacephalosaurus. Later studies have consistently supported this position. The Brachaucheninae subfamily includes most plesiosaurids from the Cretaceous period, and phylogenetic analyses often place them together. However, it seems that other lineages of thalassophonians may have survived past the Jurassic, as lower Cretaceous plesiosaur teeth show characteristics different from those of Brachaucheninae. Members of this subfamily are varied, and only one trait unites them all. Their teeth tend to be roughly circular rather than fully or partly triangular as seen in some Jurassic plesiosaurs. Many Brachauchenines, such as Megacephalosaurus, share skull features including elongated snouts, slender rostrums, and uniformly sized teeth, adaptations suited for hunting smaller prey. Kronosaurus, however, is a notable exception. Its teeth are each shaped differently, suggesting it specialized in hunting large prey, unlike most other members of its subfamily. Plesiosaurs were extraordinary marine reptiles, perfectly adapted to life in the oceans. They grew at speeds comparable to modern birds and had very high metabolisms, suggesting they could regulate their body temperature internally, a trait called homeothermy, and possibly even true warm-bloodedness or endothermy. This would have been particularly useful for plesiosaurs living in the cold waters of ancient Australia, including the giant Kronosaurus, since southern regions at the time experienced especially low temperatures. A study conducted in 2019 by the paleontologist Corinna Fleischl and her colleagues found that plesiosaurs had unusually large red blood cells, inferred from the structure of their blood vessel canals. These adaptations would have helped them dive efficiently and survive in conditions with limited oxygen. While their short tails were probably not used for swimming propulsion, they likely helped with balance and steering as they moved through the water. Kronosaurus, with its massive size, powerful body, and wide distribution, would have been the top predator of the Eromanga Inland Sea. Fossil evidence shows that it fed on other large animals. The most famous case comes from specimen QMF10113, the most complete Kronosaurus skeleton known. This individual contained the remains of a sea turtle in its stomach. The position of the turtle suggests that the Kronosaurus died after choking on its prey. Although the turtle's bones are too fragmented to determine its exact genus, its size is similar to that of Notochelone, a protostegid sea turtle widespread in Queensland during the Albian stage of the Lower Cretaceous. In 1993, Tony Thulborn and Susan Turner studied a heavily crushed skull of an elasmosaurid, now identified as Eromangosaurus. They discovered several large bite marks that matched the teeth of contemporary Kronosaurus specimens, providing the first evidence of a pliosaur hunting an elasmosaurid. Because elasmosaurids had very long necks and small heads, the injuries suggest Kronosaurus often targeted the neck region during attacks. Although there is no direct evidence of Kronosaurus feeding on other prey, it likely hunted small plesiosaurs from the Leptoclididae family as well. The smallest known Kronosaurus specimen, catalogued as QMF51291, also shows bite marks on its skull. In 2009, researcher McHenry proposed that the largest Kronosaurus could reach up to 10 meters and 5 decimeters in length, approximately 34 feet. Smaller specimens, less than 7 meters or 23 feet, were likely juveniles or subadults. McHenry suggested that the bite marks on QMF51291 may have come from an adult Kronosaurus, indicating aggressive interactions or even cannibalism, similar to behavior observed in modern crocodilians. However, it is also possible that the bites were inflicted after death. McHenry's research also explored the enormous bite force of Kronosaurus. Using biomechanical analyses, he found that this predator had one of the most powerful bites of any known animal, only slightly exceeded by some estimates of Tyrannosaurus. Based on specimen QMF10113, Kronosaurus's bite force is estimated to have been between 16,000 and 23,000 newtons, equivalent to approximately 3,600 to 5,170 pounds of force. Later research in 2014 by Pfoffer and colleagues re-estimated this range at 15,000 to 27,000 newtons, or around 3,370 to 6,070 pounds of force, similar to its Jurassic relative Pliosaurus cavani. While formidable, these forces were still far below those of the giant predatory shark Megalodon, which could generate between 93,000 and 182,000 newtons, equivalent to 20,910 to 40,920 pounds of force. All known fossils of Kronosaurus come from the Great Artesian Basin, which during the Lower Cretaceous was flooded by a shallow inland sea called the Eromanga Sea. Sedimentary evidence shows that the sea was shallow, muddy and stagnant, with cold temperatures approaching freezing. Seasonal ice may have formed in some areas. Sea temperatures during the Albian stage were somewhat warmer than during the preceding Aptian stage, but still cooler than most tropical seas. The fossil record from the Great Artesian Basin reveals a rich diversity of marine life. Invertebrates such as mollusks were common, along with free-swimming cephalopods including ammonites, belemnites and squid. The sea floor was dominated by bivalves, with gastropods and scaphopods less numerous. Other invertebrates included crinoids, decapod crustaceans, brachiopods, polychaete worms, and even glass sponges. Fish populations varied over time, being less abundant in the Albian strata, but very diverse in the Upper Aptian. These included ray-finned fish such as Australopachycormus, Richmondichthys, Flinders-ichthys, Kuyu, and Pachyrhizondontus, as well as lungfish species like Ceratodus and Neoceratodus. Sharks and other cartilaginous fish were also abundant, including Archaeolamna, Carcharius, Cretolamna, Cretoxyrina, Edaphodon, Echinohynus, Leptostyrax, Microcorax, Notorhynchus, Pseudocorax, Pristiophorus, Scapanohynchus, and others. These fish ranged from small to very large, occupying surface, mid-water and bottom-dwelling habitats, feeding on invertebrates, smaller fish, and in some cases acting as apex predators. The Eromanga Sea was home to an extraordinary variety of marine reptiles. Sea turtles included protostegids such as Cratochelone, Buliachelis, and Notochelone, the latter being the most common. Ichthyosaur fossils, initially assigned to multiple genera, are now generally identified as Platypterygius australis, one of the last ichthyosaurs known. Other plesiosaurs are represented, but many fossils are too incomplete to assign to a specific species. Kronosaurus remains are the most widespread plesiosaur fossils in Australia and the only large pliosaur known from the continent, except for the disputed genus Ichthyosaurus. Other marine reptiles included the cryptoclidid Opalionectes, elasmosaurids such as Eromangosaurus, and various Leptocleidia members like Leptocleidus and Umunosaurus, while polycotylids are represented by undetermined specimens, most notably the Richmond specimen. Even as the apex predator, Kronosaurus was not entirely safe. Fossil evidence shows that some individuals were attacked by other predators, such as large sharks from the Cretoxiohinidae family. For example, a jaw catalogued as KKF0630 shows healed bite marks, indicating the animal survived the attack. This demonstrates that despite its dominance, Kronosaurus shared its world with other powerful predators and faced threats during its lifetime. Tylosaurus, whose name means knob lizard, was a giant sea predator that ruled the oceans long before humans ever appeared. It was not a dinosaur, but a powerful marine lizard belonging to a group called mosasaurs. These animals were fierce hunters that lived in the seas during the late Cretaceous period, from about 92 million years ago until 66 million years ago, just before the Great Extinction that ended the age of dinosaurs. Tylosaurus swam through warm, ancient waters during the Turonian to Maastrichtian stages, dominating marine ecosystems with its long, streamlined body and strong jaws. Fossils of Tylosaurus have been found mainly around what is now the North Atlantic Ocean. Its remains appear in parts of North America, Europe, and even Africa, showing that it once traveled across vast stretches of ocean. In ancient times, much of central North America was covered by a shallow inland sea, and it was in these waters that Tylosaurus thrived. It likely hunted fish, smaller marine reptiles, and anything else it could overpower. Long before scientists officially studied these fossils, Native American peoples had already encountered the enormous bones weathering out of the ground. Some of these discoveries may go back to the 1500s, well before European settlers arrived. The sight of gigantic skulls and vertebrae scattered across the plains must have been astonishing. Stories from tribes of the Great Plains speak of a distant age when massive water creatures battled powerful thunderbirds in the sky. According to legend, these sea monsters were eventually struck down and turned to stone. The region where these stories were told is rich in fossils of large mosasaurs like Tylosaurus and flying reptiles such as Pteranodon. It is very possible that these ancient bones inspired such dramatic and lasting myths. In the year 1804, during the famous journey of the Lewis and Clark expedition, explorers found a large fossil skeleton near the Missouri River. The remains, which have since been lost, were described as belonging to a fish about 45 feet long, which is roughly 14 meters. At the time, little was known about giant marine reptiles, so the explorers understandably believed it was an enormous fish. In 2003, writer Richard Ellis suggested that those lost remains may have belonged to Mosasaurus missouriensis, another giant sea reptile. However, in 2007, a study led by Robert W. Meredith proposed a different idea. Based on the measurements recorded by Lewis and Clark and on fossils found in the Missouri River region, the researchers suggested that the skeleton may actually have belonged to a tylosaurine mosasaur, possibly a species of Tylosaurus. They also noted that it could have been an elasmosaurid plesiosaur, another type of long-necked marine reptile known from the same river, although such fossils are rarer there. Because the original specimen is lost, the mystery remains unsolved. Tylosaurus holds an important place in the history of paleontology. It was the third new mosasaur genus described from North America, following Clydastes and Platecarpus, and it was the first of its kind to be identified in Kansas. However, its early scientific story was filled with rivalry and confusion. During the late 1800s, two American paleontologists, Edward Drinker Cope and Othniel Charles Marsh, were locked in a fierce competition known as the Bone Wars. Each man raced to discover, name and describe as many new fossil species as possible, often arguing bitterly over classification. The first important specimen of Tylosaurus was described by Cope in 1869. It was based on part of a skull nearly 5 feet long and 13 vertebrae. The fossil had been lent to him by Louis Agassiz from the Harvard Museum of Comparative Zoology. The bones were found in the Niobrara Formation near Monument Rocks in Kansas, close to the Union Pacific Railroad at Fort Hays. At first, Cope named the fossil Macrosaurus proriger. The name Macrosaurus had already been used for a European mosasaur, and the species name proriger meant prow-bearing, referring to the long, pointed snout that looked like the front of a ship. A year later, in 1870, Cope gave a more detailed description and moved the species into another European genus called Liopleurodon. He even declared his earlier name invalid. In 1872, Marsh challenged Cope's classification. He argued that the fossil was clearly different from European forms and deserved its own new genus. He created the name Rhinosaurus, meaning nose lizard, highlighting the animal's distinctive snout. Cope objected, saying that Rhinosaurus was already too closely linked to Liopleurodon. He suggested that if a new name was truly needed, it should be Ramphosaurus instead. Soon after, Marsh discovered that Ramphosaurus had already been used for another reptile back in 1843. This forced him to create yet another new name, Tylosaurus. The name once again referred to the animal's unusual snout, using a word that means knob, combined with the Greek word for lizard. Interestingly, although Marsh created the name, he never formally transferred the species into this new genus. That step was finally taken in 1873 by Joseph Leidy. Over time, Tylosaurus became widely accepted by scientists as the correct genus for this species. The only major holdout was Cope, who stubbornly continued to use Liopleurodon in his own publications. In 1874, he even described another species and named it Liopleurodon nepaolicus. The fossil for this species had been found near the Solomon River by geologist Benjamin Franklin Mudge. It included parts of the skull and one back vertebra and is now kept under the catalogue number AMNH 1565. The species name honored Nepahola, the Native American name for the Solomon River. Finally, in 1894, John Campbell Merriam officially transferred this species into the genus Tylosaurus as well. Through scientific rivalry, lost fossils, and even ancient legends, the story of Tylosaurus is as dramatic as the predator itself. Once the terror of ancient seas, it now stands as one of the best-known and most fascinating marine reptiles of the late Cretaceous world. In his important study published in the year 1967, Dale A. Russell concluded that only 2 true species should be recognized within the giant marine reptile genus Tylosaurus. These were Tylosaurus proriger and Tylosaurus nepaolicus. At the time, many other fossils from different parts of the world had been given their own separate genus names during the 19th and 20th centuries. But as more research was done and scientists compared bones more carefully, many of these supposedly different sea reptiles were found to actually belong to Tylosaurus. What once seemed like a scattered group of unrelated marine monsters slowly came together under one name. Back in the year 1885, the Belgian paleontologist Louis Dollo described a large sea reptile from an almost complete, though badly preserved skeleton found in a phosphate quarry in the Sipley Basin. He named it Hinosaurus bernardi. The name Hinosaurus means lizard from the Haine, referring to a nearby river, while the species name honored Leopold Bernard, the man who made the excavation possible. The fossil later received the catalogue number IRSNBR23. For many years, Hinosaurus was considered a separate genus. More than a century later, in the year 1988, Elizabeth Nichols described another species connected to Hinosaurus. This fossil, catalogued as MT2, came from Manitoba and was found in a rock layer known as the Pembina member of the Pierre Shale. The species was named Hinosaurus pembinensis after the place where it was discovered. Years later, in 2005, Johan Lindgren discussed whether this animal truly belonged in Hinosaurus. Then, in a major revision published in 2010, Timon Bullard and Michael Caldwell moved the species into Tylosaurus, renaming it Tylosaurus pembinensis. They also suggested that the original species, Hinosaurus bernardi, needed to be studied again to determine whether Hinosaurus truly deserved to remain a separate genus. That careful re-examination finally happened in 2016 when Paulina Jimenez Huidobro and Caldwell reviewed the material and concluded that Hinosaurus bernardi should also be moved into Tylosaurus, becoming Tylosaurus bernardi. Although many scientists accepted this change, some researchers still argue that Hinosaurus should remain separate, pointing especially to differences in the teeth that were not fully discussed in the 2016 revision. The debate shows how even small details like the shape of a tooth can reshape the family tree of giant marine predators. Earlier still, in the year 1896, Armand Thévenin described another marine reptile from a partial skull discovered at Éclusiers-Vaux in the Somme region of France. The fossil, catalogued as MNHN 1896-15, was first named Mosasaurus gaudriae in honor of his mentor Jean-Albert Gaudry. Gaudry had earlier studied the skull and believed it belonged to a different marine reptile called Liopleurodon. Decades later, in 1992, Thiergarten Lingham Solier reassigned the species to Hinosaurus. Then, in 2005, Lindgren transferred it again, this time into Tylosaurus, mainly because its teeth more closely matched other members of that genus. With each new study, the identity of this ancient predator shifted slightly, like pieces of a puzzle being rearranged. In the year 1963, Per over Persson identified another mosasaur based on isolated teeth found at Evo Klack near Evo Lake in the Kristianstad Basin of Scania, Sweden. Fossils from that region had been known since the year 1836, and they were once described as a subspecies of Mosasaurus hoffmanni, named Mosasaurus hoffmanni evoensis after the locality. In 1967, Russell raised it to full species level within Tylosaurus and linked additional fossils from the Niobrara Formation of Kansas to it. However, in 2002, Lindgren and Mikael Siversen carefully reviewed the material, reassigned the species to Tylosaurus, and showed that the Kansas fossils Russell had connected to it actually belonged to a different species. Later, in 2008, Caldwell and colleagues suggested that Tylosaurus ivoensis might instead belong to another related genus called Taniosaurus, based on its teeth and where its fossils were found, though they left that question open for future research. In the year 1964, Miguel Teles Antunes described Mosasaurus iembensis from a partial skull discovered in the Itombe Formation near the town of Iembe in Angola. In 1992, Lingham Solier argued that the skull's features matched Tylosaurus more closely than Mosasaurus, and the species was renamed Tylosaurus iembensis. Sadly, the original skull, which was believed to be kept at Nova University Lisbon, was later reported destroyed in a fire in 2006. In 2012, Octavio Mateus and colleagues announced that another specimen from the same location had been found, offering hope that this African species could still be better understood. In 2005, Michael J. Everhart described Tylosaurus kansasensis based on several fossils from the Niobrara Formation of Kansas. The main specimen, catalogued as FHSM VP-2295, included a beautifully preserved skull and 6 neck vertebrae and had originally been discovered in 1968 in Ellis County. However, its status soon became controversial. In 2007, Caldwell questioned whether it was truly a separate species. Then, in a major 2016 study led by Jimenez Huidobro, the authors argued that it was actually a young individual of Tylosaurus nepaiolicus, making the name Tylosaurus kansasensis unnecessary. Everhart disagreed in a 2017 book, criticizing the study but without fully explaining why. Later reviews in 2018 and 2020 reached different conclusions, with some researchers supporting its validity and others preferring to treat it as part of Tylosaurus nepaiolicus. The disagreement highlights how growth stages in ancient animals can make classification especially difficult. In 2006, Bullard wrote a Master of Science thesis describing Tylosaurus saskatchewanensis from a partial skeleton known as RSMP 2588.1 found in the Bearpaw Formation. The specimen, nicknamed Omak W, meaning hunter in the Cree language, had been discovered in 1994 near Herbert Ferry at Lake Diefenbaker in Saskatchewan. Although first described informally, it was later formally studied and confirmed as a distinct species in 2018. Finally, in 2020, Samuel Garvey studied a partial skull from the Postcranial Formation of Alberta, about 55 kilometers northeast of Grande Prairie. Because of its northern location and unique features, he informally referred to it as Tylosaurus borealis, meaning the northern Tylosaurus. This specimen represents the northernmost known example of the genus so far, showing just how far these massive marine predators once roamed across the ancient seas. When Edward Drinker Cope first described the main specimen of Tylosaurus proriger in the year 1870, he imagined it as a very long and stretched-out reptile, based largely on the shape of its tail vertebrae, which gave that impression. According to his early descriptions, this would have made the animal resemble a kind of sea serpent, stretching to lengths comparable to the largest whales alive today. The following year, Cope added more details to his vision of the creature. He thought the head of Tylosaurus would have been cone-shaped, with eyes positioned on top, and a jaw connected to a throat similar to that of a pelican, which would have allowed it to swallow prey more easily. Cope also believed that Tylosaurus had only front flippers, with the back ones missing entirely. Its tail, in his view, was long and flat, moving in a way similar to how eels swim. This image of Tylosaurus was widely repeated in many works during the late 19th century, though some depictions also gave it a long, snake-like neck. A major revision of mosasaurs in the year 1898 by Samuel Wendell Williston corrected many of these early misconceptions. He offered a new, more accurate description of Tylosaurus, focusing on 3 partial specimens housed at the University of Kansas Natural History Museum. Williston's skeletal reconstruction portrayed Tylosaurus as a highly agile marine predator with 4 flippers, a short neck, and a tail far shorter than what Cope had imagined. He also provided a maximum body length that is still widely cited today, approximately 11 meters long. In this reconstruction, the spine was drawn straight rather than curved, but it remains scientifically valid even today. The first nearly complete skeleton of Tylosaurus was discovered shortly afterward, in 1899 by Henry Fairfield Osborn, with similar finds following in the early years of the 20th century. Tylosaurus was an advanced type of mosasaur, a later evolving group that had fully adapted to life in water. It had a streamlined body, a long tail ending in a downward bend that supported a 2-lobed fin and 2 pairs of flippers. While older interpretations compared these derived mosasaurs to giant sea snakes, modern understanding shows they were more similar in body structure to large marine reptiles like ichthyosaurs, marine crocodiles, and early whales, due to a process called convergent evolution, where unrelated animals evolve similar features. Some Tylosaurus species were among the largest mosasaurs ever known. The largest well-documented specimen, a skeleton of Tylosaurus proriger nicknamed Bunker at the University of Kansas Natural History Museum, has been estimated at between 12 and 15.8 meters in length. Another partial skeleton of T. proriger from the Sternberg Museum of Natural History may have belonged to an even larger individual. Estimates suggest it could have reached 14 meters in length compared to the 12 meters estimated for Bunker. Over time, Tylosaurus followed Cope's rule, meaning its body size tended to increase across geologic periods. In North America, the earliest Tylosaurus species, living during the Turonian and Coniacian stages, roughly 90 to 86 million years ago, such as early Tylosaurus nepaolicus and its ancestors, measured around 5 to 7 meters long and weighed between 200 and 500 kilograms. By the Santonian stage, About 86 to 83 million years ago, T. nepaolicus and the newly emerging T. proriga reached lengths of 8 to 9 meters and weighed roughly 1,100 kilograms. During the early Campanian stage, T. proriga grew even larger, attaining lengths of 13 to 14 meters. Some paleontologists have speculated that exceptionally old individuals could theoretically have reached up to 20 meters, although no fossil evidence supports such extreme sizes. Other species from the Campanian to Maastrichtian stages were similarly impressive. The most recent estimate for Tylosaurus bernardi puts it at 12.2 meters in length, though earlier estimates mistakenly suggested it could be as long as 15 to 17 meters. A reconstruction of Tylosaurus saskatchewanensis by the Royal Saskatchewan Museum suggested a total length of over 9.75 meters. The mounted skeleton of Tylosaurus pembinensis, nicknamed Bruce, at the Canadian Fossil Discovery Centre measures 13.05 meters and was recognized by Guinness World Records in 2014 as the largest mosasaur on display, though later studies noted that the original assembly had slightly exaggerated its vertebral count. Tylosaurus borealis is estimated at between 6.5 and 8 meters in total length. The largest known skull belongs to the bunker specimen of Tylosaurus proriga, measuring approximately 1.7 meters long. Tylosaurus skulls generally accounted for about 13 to 14% of the total body length, depending on age and individual variation. The head was strongly conical, with a snout longer than most other mosasaurs, except for Ecktenosaurus, giving it a distinctive predatory profile. The most striking and easily recognizable feature of Tylosaurus is its long, toothless snout, which gives the genus its name. This snout is formed by the front part of the upper jaw bones, known as the premaxilla, and the lower jaw bones called the dentary. When Tylosaurus was born, the snout was short and sharply pointed, but as the animal grew, it quickly transformed into a blunt, elongated knob, giving it a distinctive appearance. The snout itself was very strong, supported by a broad and solid structure between the nostrils, called the internarial bar, which includes parts of the premaxilla, the nasal bones, and the front part of the frontal bone. This heavy construction allowed the snout to house branches of the trigeminal nerves, which passed through small scattered openings along the snout and just above the gum line of the upper jaw. The openings of the nostrils, or external nares, were bordered by the premaxilla, maxilla, and frontal bones. Unlike in other mosasaurs, the prefrontal bones did not touch the nostril edges because a long extension of the maxilla separated them. The exact position of the nostrils varied slightly by species. In Tylosaurus proriga and Tylosaurus pembinensis, they were located above the fourth tooth of the upper jaw. In Tylosaurus nepaolicus, they appeared between the third and fourth teeth, and in Tylosaurus bernardi, they were just behind the fourth tooth. The relative length of the nostrils compared to the skull also differed between species. In Tylosaurus proriga, the nostrils were relatively short, about 20 to 27% of the skull's total length. In Tylosaurus bernardi, they measured about 24%, and in Tylosaurus gardrii, around 25 to 27%. Meanwhile, Tylosaurus pembinensis had proportionally long nostrils, making up 28 to 31% of its skull length. The nasal bones themselves were either loosely connected or free-floating above the internarial bar, never touching the frontal bone, and never fused together as they are in modern monitor lizards. Because these bones were not firmly attached, they were often lost over time, which is why they are so rarely preserved. Tylosaurus is one of the few mosasaurs where the nasal bones have been clearly identified. The only other example is the holotype of Plotosaurus, though one of its nasal bones is missing. The external nostrils connected to the internal nostrils, called the choanae, located in the roof of the mouth. These passageways allowed air to travel from the nostrils to the throat. In Tylosaurus, the choanae were shaped like compressed teardrops, and were surrounded by the vomer bones, palatine bones, and maxilla. Just in front of these internal nostrils, each vomer bordered an opening for the Jacobson's organ, a structure used for sensing smells through the tongue. In Tylosaurus, this organ began opposite the fourth upper tooth, and in Tylosaurus bernardi ended just past the fifth tooth. Veins leading to sinuses inside the roof of the mouth exited just in front of the Jacobson's organ between the vomer and the maxilla, which differs from modern monitor lizards, where these veins exit behind the organ. The frontal bone of Tylosaurus often, but not always, had a low crest running along the middle. This crest was most pronounced in Tylosaurus proriga, moderately visible in Tylosaurus saskatchewanensis and Tylosaurus bernardi, and in the latter, it even extended onto the premaxilla. In Tylosaurus nepaiolicus, the crest was usually small and sometimes disappeared entirely in fully grown individuals. The frontal bone overlapped the prefrontal and postorbitofrontal bones above the eyes and connected to the parietal bone at the back. The small pineal eye on the parietal could appear either close to or touching the frontoparietal joint. The eye sockets were bordered by the prefrontal, lacrimal, postorbitofrontal, and jugal bones. A unique feature of Tylosaurus is that the prefrontal and postorbitofrontal bones overlap above the eye sockets, preventing the frontal bone from contributing to this border. The jugal bone formed the lower edge of the eye socket. In Tylosaurus, it had an L shape with a distinctive small projection at the back corner, known as the posteroventral process. The vertical part of the jugal was usually overlapped by the postorbitofrontal in most species, while the horizontal part overlapped the maxilla. In Tylosaurus bernardi, the vertical part did not overlap but joined the postorbitofrontal with a suture and was much thicker than the horizontal part. At the back of the skull were the quadrate bones, which connect the lower jaw to the skull and hold the eardrums. The quadrate is complex and varies enough to help identify Tylosaurus down to the species level. In side view, the quadrate of young Tylosaurus nepaiolicus and Tylosaurus proriga looked like a hook, but in adults of these species, and in Tylosaurus bernardi, Tylosaurus pembinensis, and Tylosaurus saskatchewanensis, it became a thick, oval-like shape. The eardrum attached to a shallow or deep depression on the bone called the ala conch, depending on the species. The rim of this conch was thin in Tylosaurus nepaiolicus, Tylosaurus proriga, and Tylosaurus bernardi, and thick in Tylosaurus pembinensis and Tylosaurus saskatchewanensis. Extending from the quadrate was the suprastapedial process, a hook-like projection that likely served as the attachment point for the jaw-opening muscles. In young Tylosaurus nepaiolicus and Tylosaurus proriga, this process was long and slender, but it thickened with age. Its length in Tylosaurus saskatchewanensis was similar to that in Tylosaurus proriga, but it was shorter in Tylosaurus bernardi. In Tylosaurus pembinensis, it turned sharply downward at a 45-degree angle. Another projection, the infrastapedial process, emerged from the lower back edge of the alar conch and changed shape as the animals grew. In Tylosaurus nepaiolicus, it was absent in juveniles but appeared as a small bump in adults. In Tylosaurus proriga, it was a small point in young animals and developed into a broad semicircle in adults. In Tylosaurus bernardi, it remained small, and in Tylosaurus pembinensis and Tylosaurus saskatchewanensis, it was rounded. In Tylosaurus saskatchewanensis, the suprastapedial and infrastapedial processes nearly touched. At the bottom of the quadrate was the mandibular condyle, a rounded joint connecting the quadrate to the lower jaw. On the inside surface of the quadrate, a thick, pillar-like ridge often projected beyond the top edge of the bone, making it visible even from the side. The upper jaws of Tylosaurus were made up of two main bones called the premaxilla and the maxilla, while the lower jaws were composed of several bones: the dentary, splenial, coronoid, angular, surangular, and the prearticular articular, which is a fused bone similar to what is seen in other lizard-like reptiles. The teeth along the edges of the mouth, known as the marginal teeth, were found in the premaxilla, maxilla, and dentary, whereas the teeth on the roof of the mouth, called palatal teeth, were located on the pterygoid bones. On each side of the skull, Tylosaurus had 2 teeth in the premaxilla, 12 to 13 in the maxilla, 13 in the dentary, and 10 to 11 on the pterygoids. All of its teeth were generally homodont, meaning they were almost identical in size and shape, except for the pterygoid teeth, which were smaller and more curved backward than the marginal teeth. The lower jaw, particularly the dentary bone, was long and strong. In adult Tylosaurus nepaiolicus and Tylosaurus proriger, the dentary made up slightly more than half, about 56 to 60%, of the total length of the lower jaw. In Tylosaurus pembinensis, it was around 55%, and in Tylosaurus saskatchewanensis, it accounted for about 62%. The dentary was sturdy, though not as heavily built as in some of its close relatives like Mosasaurus, Prognathodon, or Plesiotylosaurus. Its lower edge ranged from straight to slightly curved inward. In adult Tylosaurus proriger, a small ridge could be seen on top of the dentary just in front of the first tooth. The teeth along the edges of the mouth were mostly adapted for slicing large marine animals. However, in species like Tylosaurus ivoensis and Tylosaurus gordrai, the teeth seemed better suited for piercing or smashing prey, while Tylosaurus borealis had teeth capable of both cutting and piercing. The teeth were triangular and curved slightly backward, forming a gentle U-shaped curve toward the tongue. When viewed from above, they appeared compressed from the tongue side and the lip side, giving them an almost oval appearance. In young Tylosaurus proriger, the teeth started out compressed but became more conical as the animal grew. The cutting edges of the teeth, called carinae, were finely serrated with tiny notches, although juveniles of Tylosaurus nepaiolicus did not have serrations, and in Tylosaurus pembinensis they were very faint. Most teeth had carinae on both the front and back edges, though some in the front might only have carinae on the front. The placement of these edges was not always symmetrical. In species like Tylosaurus proriger, Tylosaurus ivoensis, Tylosaurus gordrai, and Tylosaurus pembinensis, the tongue side had more surface area than the lip side. In Tylosaurus bernardi, both sides were always evenly balanced. The enamel covering the teeth had thin vertical ridges called striations that ran from the base to near the tip, and the surface could be smooth or slightly flattened to create a prism-like shape. Researchers in 2006 divided Tylosaurus species into 2 groups based on their marginal teeth. The first group, called the North American proriger group, included Tylosaurus proriger and Tylosaurus nepaiolicus. Their teeth had smooth or faintly flattened surfaces, less prominent carinae, and primitive vein-like striations that extended nearly to the tip. These teeth were once thought to be slender, but later studies showed that young Tylosaurus proriger had slender teeth that became more robust in adults. Tylosaurus saskatchewanensis, although not formally part of this group, had similar teeth to Tylosaurus proriger. The second group, called the Euro-American ivoensis group, included Tylosaurus ivoensis, Tylosaurus gordrai, and Tylosaurus pembinensis. Their teeth were thick and strong, with noticeable cutting edges and striations along the tongue side and sometimes the lip side, though these striations did not reach the tip. The surfaces on the lip side were flattened into gentle facets, slightly concave in Tylosaurus ivoensis, a feature also known as fluting. The teeth of Tylosaurus gordrai were almost identical to Tylosaurus ivoensis. Another species, Tylosaurus iambensis, was not placed in either group and is only known to have striated teeth without facets. Some scientists debate whether this ivoensis group is valid because, for example, Tylosaurus pembinensis lacks fluting, and Tylosaurus ivoensis may be more closely related to another fluted-toothed genus called Taniosaurus. The pterygoid teeth on the roof of the mouth may have helped Tylosaurus hold prey in place, while the lower jaw moved back and forth in a ratcheting motion. The base of each pterygoid tooth was nearly circular, and most had faint front and back cutting edges dividing the tooth into nearly equal surfaces. In Tylosaurus, these teeth were flattened from side to side. Unlike the marginal teeth, the pterygoid teeth did not have serrated edges. The front surfaces were usually smooth or slightly flattened, while the back surfaces were striated. In adult Tylosaurus, both the pectoral and pelvic girdles remained separate and unfused, unlike in some other mosasaurs, such as Prognathodon overtoni, where the bones are fused. This separation was one of several traits that distinguished Tylosaurus from its relatives. Its shoulder blade or scapula was noticeably smaller than the coracoid bone, and unlike other mosasaurs, Tylosaurus lacked a front-facing notch in the coracoid and did not have a prominent pubic tubercle. The limbs of Tylosaurus were relatively primitive compared to those of more advanced mosasaurs. The upper limb bones, the humerus in the forelimbs and the femur in the hind limbs, lacked the complex muscle attachment areas and extreme shortening seen in later mosasaurs. Additionally, many of the wrist and ankle bones remained mostly unossified, meaning they did not fully turn into bone. While most adult mosasaurs developed between 3 and 5 ossified carpal and tarsal bones, adult Tylosaurus never had more than 2 in each limb. Usually, the forelimbs had only the ulnar, and sometimes the ulnar along with the 4th distal carpal, while the hind limbs had only the astragalus, and sometimes the astragalus together with the 4th distal tarsal. Another unique feature was hyperphalangy, or having extra finger and toe bones in both the front and back limbs. These phalanges were long and spindle-shaped, in contrast to the short, blocky, hourglass-shaped bones seen in mosasaurines. In addition, the pisiform, a small wrist bone, was either missing or unossified. While these differences are clearly visible in fossils, scientists are still uncertain how they affected the swimming and movement abilities of Tylosaurus compared to other mosasaurs. The backbone of Tylosaurus consisted of between 29 and 30 vertebrae before the sacrum, 6 to 7 pygal vertebrae near the base of the tail, and an impressive 89 to 112 tail vertebrae. Because the ilium, part of the hip, did not connect directly to the backbone, it remains unclear whether any mosasaurs had true sacral vertebrae like land reptiles. In all Tylosaurines, similar to plioplate carpines, the chevrons, bones along the underside of the tail, were attached to the tail vertebrae but not fused to them, as is seen in mosasaurines. The tail of Tylosaurus curved downward noticeably, suggesting it supported a tail fluke that helped with swimming. Fossilized skin impressions of Tylosaurus have been known since the late 1870s. These fossils show small, diamond-shaped scales arranged in slanted rows, resembling the skin patterns of modern rattlesnakes and related reptiles, but proportionally much smaller. For example, an individual measuring 5 meters in total body length had scales measuring approximately 3.3 millimeters by 2.5 millimeters, with around 90 scales packed into each square inch of its underside. Each scale had a keel, similar in structure to a shark's denticles, which likely helped reduce drag in the water and minimized reflection, making the animal more efficient and stealthy while swimming. Microscopic examination of scales from a Tylosaurus nepaolicus specimen revealed high levels of eumelanin, a pigment indicating a dark body coloration similar to that of the modern leatherback sea turtle. It is likely that Tylosaurus also had countershading, a common pattern in aquatic animals where the belly is lighter than the back, although the exact distribution of pigments is unknown. Dark coloration would have offered several advantages. It could help the animal absorb heat in cooler waters, support faster growth in young individuals, provide better camouflage from predators and prey, and possibly protect the skin from ultraviolet radiation. Interestingly, some genes associated with dark pigmentation can also increase aggression, suggesting a potential behavioral impact. A specimen catalogued as AMNH-FR 221 preserves parts of the cartilaginous respiratory system, including the larynx, trachea, and bronchi, although these were only briefly described by Osborn in 1899. The larynx was poorly preserved, beginning between the pterygoid and quadrate bones of the skull and extending slightly behind the quadrate. The trachea continued from below the atlas vertebra, but was only preserved intermittently. Further along, just below the fifth rib, the bronchi reappear as paired airways extending behind the coracoids. This pairing indicates that Tylosaurus likely had two functional lungs, similar to modern lizards with limbs but unlike snakes, which have elongated lungs. Similar branching has been observed in plate carpus and possibly Mosasaurus, the only other derived mosasaurs with fossilized respiratory systems. The branching point of the Tylosaurus trachea probably occurred somewhere between the first and sixth neck vertebrae. In plate carpus, the bronchi diverged below the sixth neck vertebra, forming nearly parallel tubes, whereas in Mosasaurus, the bronchi were positioned differently. A branching point located ahead of the forelimbs, as in Tylosaurus, is unusual compared to terrestrial lizards, where it occurs in the chest, but resembles the short trachea and parallel bronchi seen in whales. Tylosaurus is a genus of giant marine lizards that belongs to the family Mosasauridae, which is part of the larger group called Mosasauridae. It is the defining genus of its own subfamily, Tylosaurinae, which also includes other related creatures such as Taniosaurus and possibly Kaikaifilu. What sets this subfamily apart is a long, pointed snout at the front of the upper jaw called the premaxillary rostrum, which is completely toothless. The closest relatives of Tylosaurinae are the Plioplatycarpinae and the more primitive groups Tethyssaurinae and Jaguarasaurinae. Together, these groups form one of three main lineages of mosasaurs, alongside the Mosasaurinae subfamily and the Halisauromorpha group. This particular lineage was first identified in 1993 and later given the name Russellosaurina by Poulsen and Bell in 2005. Tylosaurus was among the first mosasaurs to show advanced adaptations, making it one of the earliest derived members of the family. The oldest known fossil of this genus is a piece of the front upper jaw called a premaxilla, labeled TMM 40092-27. It was found in the Arcadia Park Shale in Texas in rock layers that formed during the Middle Turonian stage, which is roughly between 92.1 and 91.4 million years ago, determined by comparison with other fossil markers. When this specimen was first described, it was only tentatively placed in the Tylosaurinae subfamily, but researchers noted it probably belonged to the species Tylosaurus kansasensis. A later re-examination in 2020 confirmed it as part of this species. Another slightly younger fossil, a skull known as SGM-M1, was discovered in the Ojinaga Formation in Chihuahua, Mexico. This skull represents an indeterminate species of Tylosaurus similar to T. kansasensis and is about 90 million years old at the earliest. Interestingly, a single tooth from the late Maastrichtian period, found in Nasiłów, Poland, dates very close to the boundary between the Cretaceous and Paleogene periods. This tooth was originally attributed to Hinosaurus, but since Hinosaurus is now considered a synonym of Tylosaurus, it shows that the genus survived until almost the very end of the age of mosasaurs. Currently, scientists recognize 8 valid species of Tylosaurus: Tylosaurus proriga, T. nepiolicus, T. bernardi, T. gardrai, T. evoensis, T. iambensis, T. pembinensis, and T. saskatchewanensis. There are 2 more species whose status is still debated. T. kansasensis might actually be the same as T. nepiolicus, and T. borealis has yet to be formally described in scientific literature. In 2020, researchers Madzia and Cao carried out a detailed analysis using Bayesian statistical methods to better understand how early mosasaurs like Tylosaurus evolved in response to other large marine predators of the time, such as pliosaurs and polycotylids. This type of analysis allows scientists to estimate rates of evolutionary change and the timing of when different groups diverged from one another. They found that the Tylosaurinae branch likely split from its closest relatives, the Plioplatycarpinae, around 93 million years ago, and this split involved the fastest evolutionary changes observed in any mosasaur lineage. These rapid changes coincided with the extinction of pliosaurs and a decline in polycotyledon diversity. The study also noticed that Tylosaurus developed some similar features to these other marine reptiles, especially in tooth shape and body size. However, there was no evidence that Tylosaurus caused the extinction of pliosaurs or polycotyledons. Instead, the researchers suggested that Tylosaurus simply took advantage of the vacant ecological roles left behind by their disappearance. Their analysis also estimated that T. nepiolocus diverged from other Tylosaurus species around 86.88 million years ago, and that T. proriga and T. bernardi split from each other around 83.16 million years ago. The study also indicated that Tanyosaurus may have diverged from Tylosaurus around 84.65 million years ago, though this result does not fully match previous family tree studies. In the western interior seaway, evidence suggests that T. nepiolocus and T. proriga may actually represent a single evolving lineage, called a chronospecies, where one species gradually changes into another without branching. This idea is supported by the fact that their fossil layers do not overlap, they are closely related, share small intermediate differences like changes in the quadrate bone of the skull, and lived in the same regions. Scientists have proposed two possible explanations for how this evolutionary change happened through alterations in growth patterns. First, in 2016, Jimenez Huidobro, Simoes and Caldwell suggested that T. proriga evolved as a pedomorph of T. nepiolocus. In other words, the new species may have developed by keeping certain juvenile traits of its ancestor into adulthood. They based this on features like a frontal crest and the curved edges of the parietal bone, which appear in young T. nepiolocus and in all T. proriga, but are lost in adult T. nepiolocus. Later, in 2020, Zietlow studied growth patterns and concluded that the evidence for pedomorphosis was unclear, possibly because there were too few adult specimens to make a strong statistical claim. Zietlow also proposed an alternative scenario called peramorphosis, in which T. proriga developed traits seen in mature T. nepiolocus at an earlier stage of life. By analyzing 74 Tylosaurus specimens, Zietlow identified multiple traits present in all T. proriga and mature T. nepiolocus, but absent in juvenile T. nepiolocus, such as large and deep skulls, an elongated snout longer than 5% of the skull's total length, thick processes on the quadrate bone, a converging overall quadrate shape, and a fan-like projection on the back lower part of the quadrate. In 1967, Russell first suggested that the long, pointed snout of Tylosaurus might have been used either to stun prey or to defend itself against sharks, though he did not provide much detail about how this worked. Later, in 1992, Lingham Solier expanded on this idea in a review of Tylosaurus biomechanics. He noticed that the bone connecting the nostrils, called the internarial bar, was unusually strong for a mosasaur and joined to the frontal bone with deep interlocking structures. This created a large contact area that could resist bending, shearing, and breaking forces more effectively. Essentially, it would allow the snout to absorb and distribute the shock from blunt impacts. In Tylosaurus bernardi, Tylosaurus gordrai, and even in some early forms such as Tylosaurus nepiolocus, the joint between the front upper jaw, premaxilla, and the main upper jaw, maxilla, was reinforced with a double buttress. This acted like a locking mechanism, allowing the snout to function as a rigid strut during frontal impacts. Lingham Solier concluded that these features meant Tylosaurus could have used its snout as a battering ram. He compared this to modern behaviors, such as crocodiles ramming each other during fights, bottlenose dolphins striking sharks to kill or scare them, and orcas hitting prey with force. In 1998, he even suggested that a subadult Mosasaurus skull, which had a fractured brain case, showed evidence of being rammed by a Tylosaurus bernardi as the damage was localized and not spread across the rest of the skull. However, Lingham Solier argued that the long snout was probably not used for sexual display or male-to-male combat because studies of Tylosaurus skulls showed no difference between males and females in snout length. This idea was later supported by Konishi and colleagues in 2018, who found that the toothless part of the snout began growing very early in development. If it had been for sexual purposes, this early growth would not make sense, but it fits perfectly for a general use like ramming. Similarly, Zietlow in 2020 found no evidence that male and female Tylosaurus differed in snout growth. Another hypothesis suggests that the long snout acted as a sensory organ. Already noted by Russell in 1967, the toothless front of the snout had many small holes, or foramina, which housed the exits of the ophthalmic nerve, responsible for sending touch information from the skin to the brain. The idea that the elongated snout specifically enhanced sensation was first explored by Alvarez Herrera and colleagues in 2020. Using CT scans of a Taniosaurus skull, they discovered a complex network of internal nerve canals along the snout, with up to 16 branches inside the front of the premaxilla. About half of these branches exited through tiny holes on the outer surface of the snout. Later, in 2023, preliminary CT scans of a Tylosaurus nepaolicus skull by Paulina Carabajal and colleagues showed a similar dense branching pattern with many nerves exiting at the tip of the snout. This suggested that the snout may have contained a mechanosensory or electrosensory organ, similar to adaptations seen in plesiosaurs and ichthyosaurs. Some scientists also suggested that the extensive internal branching could help with blood flow and possibly even temperature regulation. Paleontologist Gordon Bell noted in 2002 that any injuries to the snout, such as from ramming, would have been extremely painful due to these nerve endings. Despite many specimens, the growth and life stages of Tylosaurus are still not well understood. Researchers face challenges because many specimens are scattered across the world, and museums are reluctant to allow studies that might damage the fossils. Still, several insights exist. Mosasaurs like Tylosaurus likely gave birth to live young, though direct evidence for Tylosaurus is lacking. Other mosasauroids, including Plioplatycarpus and Carsosaurus, show fossilized pregnant individuals, and newborn cledastes have been found in open water deposits. The youngest known Tylosaurus individual, labeled FHSM VP14845, was a newborn with a skull approximately 30 centimeters long and a total length of 2 meters and 23 centimeters, roughly 17% the size of Bunker and about 25% of the estimated maximum size of Tylosaurus nepaolicus. This newborn lacked the elongated toothless snout, which only appears in slightly older juveniles with skulls around 40 centimeters and 60 centimeters long. In 2007, Pellegrini used skeletochronology to study the growth of 2 juvenile Tylosaurus humeri. This method measures growth rings in bones, called lines of arrested growth, which form when growth slows or stops during seasonal changes. The older individual was 14 years old at death, and the younger 7 years. Both showed fast growth in the first few years of life, which slowed around year 5 or 6. These ages likely correspond to sexual maturity. Interestingly, the first-year growth rings were longer than those in related mosasaurs, suggesting Tylosaurus was born larger rather than growing faster later. Overall, the growth pattern was similar to modern monitor lizards but accelerated, likely due to higher metabolic needs in an aquatic environment. In 2018, Stewart and Mallon studied 15 Tylosaurus proriger skulls to see how different skull parts grew with age. Most skull measurements showed isometric growth, meaning they grew proportionally with the rest of the body. However, the toothless snout grew proportionally smaller with age, while the quadrate bone grew proportionally larger. Some unexpected results, such as the decreasing relative size of the snout, contradicted earlier observations that juvenile Tylosaurus had shorter snouts than adults. The researchers noted that a larger sample might reveal more growth patterns and confirmed that early studies could be limited by small numbers of specimens. In a study conducted in the year 2020, researcher Zietlow used a method called cladistic analysis to examine how the skulls of 3 species of Tylosaurus, Tylosaurus proriger, Tylosaurus nepaiolicus, and Tylosaurus kansasensis, developed as they grew. This method allowed him to create detailed growth charts, called ontograms, based on 79 fossil specimens. These charts showed how the shapes and structures of the skull changed as the animals matured, although they did not assign these changes to specific ages. For Tylosaurus proriger, the ontogram revealed 17 distinct growth stages. Among the most noticeable changes were the appearance of bony projections on multiple skull bones, a reduction in the size of the premaxillary openings, the hardening of bones like the basioccipital and quadrate, the reshaping of the joint between the premaxilla and maxilla into a distinct M shape, and a proportional increase in tooth size compared to the rest of the skull. For Tylosaurus nepaiolicus and Tylosaurus kansasensis, Zietlow combined specimens into a single ontogram to test whether these were truly separate species. The results suggested that there was no clear distinction between them. Instead, the Tylosaurus kansasensis fossils represented earlier growth stages, while Tylosaurus nepaiolicus fossils were from later stages, spanning a total of 12 growth series. Key changes observed included enlargement of bony projections on several skull bones, widening of the premaxillary openings, changes in the shape of the pterygoid bone, hardening of the quadrate with a transformation from a hook-like to an elongated shape, the emergence of the M-shaped premaxilla-maxilla joint, the development of an extradentary tooth, and a general increase in tooth size relative to the skull. In both ontograms, skull size grew consistently through all stages, and in Tylosaurus proriger, skull depth also increased steadily. Statistical analyses confirmed that total skull length and the height of the quadrate bone were reliable indicators of maturity in these species. Interestingly, no evidence of differences between males and females was found in the skulls. Zietlow suggested that this absence might be due to either the limited number of specimens studied or because sex-related features did not appear in the skull at all. While most lizards are cold-blooded, relying on outside temperatures to regulate their body heat, mosasaurs like Tylosaurus appear to have been warm-blooded or endothermic, which is extremely rare among reptiles. The only modern lizard with partial warm-blooded traits is the Argentine black and white tegu. In a study published in the year 2016, researchers Harrell, Perez Huerta and Suarez analyzed oxygen isotopes in Tylosaurus bones to estimate its internal body temperature. By comparing isotope levels in 11 Tylosaurus specimens with those of contemporary cold-blooded fish such as Encodus, sea turtles like Toxocolis, and the warm-blooded seabird Ichthyosaurus, they calculated an average internal temperature of 34.3 degrees Celsius or 93.7 degrees Fahrenheit. This was much higher than the temperatures of Encodus and Toxocolis, which were 28.3 degrees Celsius, 82.9 degrees Fahrenheit, and 27.2 degrees Celsius, 81.0 degrees Fahrenheit respectively, and close to Ichthyosaurus at 38.6 degrees Celsius, 101.5 degrees Fahrenheit. Similar calculations for other mosasaurs, including Platecarpus and Clydastes, produced comparable results of 36.3 degrees Celsius, 97.3 degrees Fahrenheit, and 33.1 degrees Celsius, 91.6 degrees Fahrenheit. Since these other mosasaurs were much smaller yet maintained similar temperatures, it is unlikely that Tylosaurus achieved its warmth through gigantothermy. Being warm-blooded would have given Tylosaurus several advantages, including more stamina to hunt over large areas, the ability to enter colder waters, and better adaptation to the gradual global cooling during the late Cretaceous. Earlier interpretations suggested that Tylosaurus swam like an eel, undulating its entire body. However, more recent research shows that it used carangiform locomotion, meaning most of its movement came from the tail while the upper body remained relatively stiff, similar to modern mackerel. This was supported by a statistical reconstruction of its tail fin by Song and Lindgren in the year 2025, which revealed a shape resembling that of carangiform sharks. A study by Jesse Carpenter in the year 2017 examined Tylosaurus proriger vertebrae and found that the dorsal vertebrae were quite rigid, while the neck, hip and tail regions were more flexible. This pattern differed from more advanced mosasaurs such as Plotosaurus, whose spines were stiff along most of the body. Fascinatingly, juvenile Tylosaurus proriger had stiffer neck and dorsal vertebrae than adults, which may have been an evolutionary adaptation. A rigid tail allows for faster swimming, helping young individuals escape predators or catch prey. Adults, being less vulnerable, developed more flexible spines as speed became less critical. Tylosaurus likely hunted by ambush. Its body was lightweight for its size, with small pectoral and pelvic bones and paddles that minimized weight. Its bones were highly porous and probably filled with fat cells, further increasing buoyancy. This combination made Tylosaurus energy efficient, allowing it to travel between ambush sites quietly over long distances and to strike quickly at prey using its long, powerful tail. Notably, these traits were not just due to large size, as other similarly sized mosasaurs, such as Mosasaurus hoffmanni, did not have porous bones. The reduced body density also enabled rapid acceleration during attacks, giving Tylosaurus a deadly advantage as a predator. In 1988, a study conducted by Judith Massari aimed to determine how fast Tylosaurus could swim without getting tired, known as its sustained swimming speed. She used a series of mathematical models that combined estimates of how water resistance affected the animal, how efficiently it moved, and the energy it would have used. Massar focused on two specimens of Tylosaurus proriger, one measuring 6.46 meters, roughly 21 feet 2 inches long, and the other 6.32 meters, about 20 feet 7 inches. Her calculations suggested that this giant sea predator could maintain a steady speed of 2.32 meters per second, equivalent to around 5 miles per hour. However, when tested, the models appeared to overestimate the speed. This was largely because the drag, the resistance from water, might have been underestimated. Calculating drag for an extinct animal is tricky, as it requires guessing the shape and size of a creature that no longer exists. Massare concluded that the real swimming speed of Tylosaurus was probably closer to half of her calculated figure. Tylosaurus was among the largest marine predators of its era, ruling as an apex predator over a diverse ocean ecosystem. Its diet is well documented from fossils, showing that it fed on other mosasaurs, plesiosaurs, sea turtles, birds, bony fish, and sharks. Bite marks on fossils also suggest that it attacked giant squid and ammonites, showing that it was capable of taking on dangerous and fast-moving prey. The massive appetite of Tylosaurus is exemplified by a remarkable discovery in 1987, when a single T. proriger skeleton, catalogued as SDSM 10439 from the Pierre Shale of South Dakota, was found with the remains of multiple animals in its stomach. These included a mosasaur over 2 meters long, the diving bird Hesperornis, a fish called Bananogmius, and possibly a shark. Other stomach contents discovered in various Tylosaurus specimens reveal similar behavior: a sea turtle in a T. bernardi-like species, a Dolichor hinchops measuring 2.5 meters inside an 8-meter 8-inch T. proriger, partially digested bones and scales of a fish called Similichthys, vertebrae of another mosasaur named Clydastes, the remains of 3 plate carpus individuals in T. nepaolicus, and bones of Plioplatycarpus in T. saskatchewanensis. In addition, puncture marks on ammonites, the shell of the sea turtle Protostega, and the internal shell of the giant squid Entrateuthis are attributed to attacks by Tylosaurus. An unusual case comes from a study by Pash and May in 2001, which reported bite marks on a dinosaur skeleton known as the Talkeetna Mountains hadrosaur. This fossil was found in marine sediments of the Turonian age Matanuska Formation in Alaska. The bite marks closely matched the teeth of T. pruriga. Since the fossil was located in oceanic deposits, the researchers suggested the dinosaur had floated out to sea after dying, and the mosasaur scavenged its carcass. However, this idea has been disputed. Garvey in 2020 argued there was not enough evidence to support this claim, noting that T. pruriga appeared later in the Santonian and was mainly found in the western interior seaway. Still, related species were present in nearby regions, as fragmentary fossils of a Tylosaurian have been found in Turonian deposits in the Russian Chukotsky district. Tylosaurus also appears to have been aggressive toward its own kind. Fossils with injuries caused by other Tylosaurus are known, especially from the late 19th and early 20th centuries. Many of these injuries show healed bite marks, mainly around the head, suggesting non-lethal fights. Scientists speculate that these interactions could have been for courtship, similar to how some modern lizards gently bite a mate's head, or for territorial disputes, where males bite each other's heads to assert dominance. At least one case of deadly combat between Tylosaurus individuals is well documented. The holotype of Tylosaurus kansasensis, measuring around 5 meters or 16 feet, shows clear signs of being killed by a larger Tylosaurus. Its skull bears 4 large gouges, and the jaw has at least 7 puncture wounds, indicating bites from a bigger mosasaur about 7 meters long or 23 feet. The largest bite marks were roughly 4 centimeters long, matching the size of large mosasaur teeth. The neck vertebrae were twisted at an unnatural 40-degree angle relative to the skull, suggesting the animal's neck was violently turned during a fight. In a reconstructed scenario, the larger Tylosaurus likely attacked from slightly below the left side of the victim's head, causing the skull to roll and enabling the aggressor to bite the skull roof and lower jaw. This attack would crush bones, twist the jaw, detach the quadrate, and sever the spinal cord at the base of the skull, causing rapid death. Rothschild and Martin in 2005 studied 12 Tylosaurus skeletons from North America and 1 Tylosaurus bernardi skeleton and discovered that every single one showed signs of a condition called a vascular necrosis. This is a type of bone damage that happens when blood flow is restricted, and in aquatic animals it often arises from what is called decompression illness. This condition occurs when nitrogen bubbles form in the bones due to breathing air that is compressed at depth, either from diving deeply many times or from repeated dives with short recovery periods at the surface. The evidence suggests that these Tylosaurus individuals developed a vascular necrosis because of such diving behaviors. Since the condition appeared in every studied Tylosaurus, it seems likely that deep or repeated diving was a normal part of the genus's behavior. Their research showed that roughly 3 to 15% of the vertebrae in the spine of North American Tylosaurus and about 16% of the vertebrae in T. bernardi were affected by this bone condition. Later, Carlson in 2017 proposed that Tylosaurus might have developed a vascular necrosis because it did not have all the special adaptations needed for safe, deep or repetitive diving, although the genus did possess well-developed eardrums that likely offered some protection from sudden pressure changes. Some Tylosaurus skeletons also show unnatural fusion of vertebrae in their tails. In certain cases, multiple fused vertebrae cluster at the tip of the tail, forming what researchers call a club tail. Rothschild and Everhart in 2015 examined 23 North American Tylosaurus skeletons and 1 T. bernardi skeleton and found that 5 of the North American specimens had fused tail vertebrae. None of the T. bernardi skeletons showed this, but because the sample size was so small, it cannot be completely ruled out. Vertebrae fuse when the bone repairs itself after injury or disease, but the exact causes can differ from one individual to another. In one young Tylosaurus with a club tail, a shark tooth was embedded in the fused vertebrae, proving that at least some of these fusions were caused by infections following predator attacks. Most vertebral fusions in Tylosaurus were due to bone infections, but some might have resulted from joint diseases such as arthritis. However, joint disease appears to have been rare in Tylosaurus when compared with other mosasaurs like Plioplatycarpus and Clydastes. Similar bone remodeling is also seen in healed fractures elsewhere in the body. For example, one Tylosaurus kansasensis specimen had 2 completely healed ribs, and a T. proriga skull showed a fractured snout, likely from ramming a hard object like a rock. These healed injuries show that the animal survived for some time after the trauma, even though it probably experienced significant pain. Over its roughly 20 million year history, Tylosaurus lived primarily in the North Atlantic Circle Basin, which included the North Atlantic Ocean and nearby waters such as the Western Interior Seaway in North America and the Mediterranean Tethys in Europe above 30 degrees north latitude. Most of this region had a temperate ocean climate, though there are a few exceptions in warmer low-latitude regions reported in scientific literature. These include T. iambensis from the coniation of Angola, a single tooth from the Maastrichtian of the Democratic Republic of the Congo, suggested to belong to a possible Hinosaurus, and a specimen near the Cretaceous-Paleogene boundary from the Ouled Abdoun Basin in Morocco. Evidence from rock layers in the Western Interior Seaway does not clearly show whether Tylosaurus preferred specific habitats. Russell, in 1967, suggested that Tylosaurus from the Niobrara Formation lived in open waters far from shore, perhaps up to 250 miles from the nearest coastline. This is supported by certain features in their bones, which indicate adaptation to deep waters. For example, osteoporosis, a condition where bones become less dense, naturally occurs in modern deep-diving or fast-swimming animals due to bone growth in low-gravity-like conditions created by these lifestyles. Tylosaurus also had high fat deposits within its bone microstructures, which, combined with osteoporosis, would have helped it maintain neutral buoyancy in deeper water. However, later studies found Tylosaurus remains throughout both shallow and open water deposits of the Niobrara Formation. In another region, Kiernan, in 2002, found that Tylosaurus made up nearly 58% of all mosasaurs in shallow continental shelf deposits from the Santonian to early Campanian in Alabama, but only about 8% of mosasaurs in offshore deposits of the same age. This suggests that, at least in some regions, Tylosaurus may have preferred nearshore waters. Chemical analyses of Tylosaurus fossils, however, suggest that the genus was highly adaptable and could live in a wide variety of marine habitats. Harrell and Perez Huerta in 2014 studied the ratios of rare earth elements in bones from T. proriga and other Tylosaurus species from Alabama and South Dakota. These ratios indicate that the animals lived in waters ranging from about 50 meters to more than 150 meters deep, a wider range than any other mosasaurs studied, including Clydastes, Mosasaurus, Platycarpus, and Plioplatycarpus. Further studies using carbon isotope analysis of tooth enamel by Robbins in 2010 and Poulsen and colleagues in 2025 also support the idea of Tylosaurus as a generalist. Lower carbon-13 values correlate with offshore foraging, and the results showed a wide range for both Campanian T. proriga-like teeth from Texas and T. ivoensis teeth from Sweden, suggesting that T. proriga foraged in both nearshore and offshore habitats, while T. ivoensis mostly stayed near shore but occasionally ventured offshore. Another yet undescribed Turonian specimen, a 3 to 4 meter long individual, showed a carbon-13 ratio indicating shallow waters similar to modern kelp beds. Poulsen and colleagues proposed that earlier Tylosaurus species were restricted to shallower waters but gradually expanded to offshore zones as the genus evolved larger body sizes. Elasmosaurus is an extinct marine reptile that lived in what is now North America during the Campanian stage of the late Cretaceous period. roughly between 80.6 million and 77 million years ago. It was not a dinosaur, but a type of long-necked sea reptile called a plesiosaur. The first fossil of this animal was discovered in the year 1867 near Fort Wallace in Kansas, United States. The bones were sent to the American paleontologist Edward Drinker Cope, who officially named the creature Elasmosaurus platyurus in the year 1868. The name Elasmosaurus comes from ancient Greek words meaning metal plate lizard, later often translated as thin plate reptile, referring to the plate-like bones in its chest and hip area. The species name Platyurus means flat-tailed. When Cope first tried to rebuild the skeleton, he made a dramatic mistake. He placed the skull at the end of the tail instead of at the end of the neck. This error was later pointed out by his rival, Othniel Charles Marsh, and it became one of the most famous moments in their bitter scientific feud known as the Bone Wars. Today, only one incomplete skeleton of Elasmosaurus is clearly known. It includes parts of the skull, most of the backbone, and some shoulder and hip bones that have since been lost. Although other species were once placed in this genus, scientists now recognize only one valid species. A fragmentary fossil from Germany might also belong to this animal, but this is still uncertain. Elasmosaurus was an enormous sea reptile, measuring about 10.3 meters in total length, which is about 34 feet. Its body was smooth and streamlined for swimming, with 4 large paddle-shaped limbs that acted like powerful flippers. It had a short tail, a relatively small head, and an extremely long neck that alone stretched about 7.1 meters, or roughly 23 feet. Along with its relative Albertonectes, it was one of the longest-necked animals ever known. Its neck contained 72 vertebrae, which is only 3 fewer than Albertonectes, giving it one of the highest counts of neck bones in the animal kingdom. The skull of Elasmosaurus was long and narrow, shaped like a triangle. At the front were large, sharp, fang-like teeth, perfect for grabbing slippery prey. Farther back, the teeth became smaller. It had 6 teeth in each premaxilla at the very front of the upper jaw, about 14 teeth in each maxilla behind them, and around 19 teeth in each side of the lower jaw. Most of the neck bones were flattened from side to side and had a raised ridge running lengthwise along them, which likely strengthened the neck. Elasmosaurus gave its name to the family Elasmosauridae, a group of long-necked plesiosaurs specially adapted to life in the ocean. These animals swam by moving their flippers in powerful strokes, almost as if they were flying underwater. Older drawings often showed them raising their long necks high above the surface like swans, but modern research shows their necks were not very flexible and could not bend sharply upward. Scientists are still not completely sure why they had such long necks. It may have helped them sneak up on schools of small fish or soft-bodied sea creatures without moving their large bodies too much. They likely fed on small fish and marine invertebrates, catching them with their sharp teeth. Some scientists believe they swallowed small stones, called gastroliths, which stayed in the stomach and helped grind up food. Fossils of Elasmosaurus come from the Pierre Shale Formation, rock layers formed in the Great Western Interior Seaway, a vast inland sea that once split North America in two. The story of its discovery is just as fascinating as the animal itself. In early 1867, an American Army surgeon named Theophilus Hunt Turner and an Army scout named William Comstock were exploring the rocky land near Fort Wallace while the Union Pacific Railroad was being built. About 23 kilometers, or 14 miles northeast of the fort, Turner found the bones of a huge fossil reptile sticking out of a ravine in the Pierre Shale. Even though he was not trained in paleontology, he realized he had found the remains of what he called an extinct monster. In June of that year, Turner gave 3 backbone bones to the scientist John LeConte, who carried them east for identification. In December, LeConte delivered some of these bones to Edward Drinker Cope at the Academy of Natural Sciences of Philadelphia, now known as the Academy of Natural Sciences of Drexel University. Cope immediately recognized them as belonging to a gigantic plesiosaur, larger than any he had seen from Europe. He wrote to Turner asking for the rest of the skeleton. In December 1867, Turner and others returned to the site and recovered much of the backbone, along with rock nodules containing more bones. Altogether, the material weighed about 360 kilograms, or 800 pounds. The fossils were carefully dug out of the soft shale using picks and shovels, loaded onto a horse-drawn wagon, and taken back to Fort Wallace. From there they were packed in crates padded with hay and sent by military wagon to meet the railroad. The specimen reached Philadelphia by rail in March 1868. Cope quickly examined it and announced the new species that same month. Turner continued searching for more pieces and sent additional fossils later that year. Sadly, he died unexpectedly on July 27, 1869, without seeing the full scientific impact of his discovery. Cope did not learn of Turner's death until the following year. The details of how the fossil was found remained mostly unknown until Turner's letters were published in the year 1987. Elasmosaurus became the first major fossil discovery in Kansas and triggered a rush of fossil hunting in the region, sending thousands of fossils to museums along the eastern United States. At the time, it was one of the few plesiosaurs known from North America and the first recognized member of the long-necked elasmosaur family. In 1869, Cope formally described and illustrated Elasmosaurus. However, his early reconstruction showed the animal with a short neck and a very long tail. In March 1870, the paleontologist Joseph Leidy pointed out at a scientific meeting that Cope had placed the skull on the wrong end of the backbone. Cope tried to correct the mistake by printing a revised version, but the damage was done. Marsh repeatedly reminded the scientific world of Cope's error, especially during their heated public disputes in the 1890s. Many historians have wondered how such a talented scientist could make such a simple mistake. At the time, the specimen was unique, and knowledge of plesiosaur anatomy was still developing. Cope was young, in his late 20s, and had no formal training in paleontology. Some have suggested he may have been influenced by earlier confusion over similar fossils. In the year 2002, the art historian Jane P. Davidson argued that the mistake cannot be fully excused, since enough was already known about plesiosaurs to avoid such an error. After the controversy, the fossil remained largely untouched in storage for nearly 30 years. It was not carefully studied again until the year 2005, when the German paleontologist Sven Sachs provided a detailed modern redescription. Today, Elasmosaurus remains one of the most famous marine reptiles ever discovered, not only for its astonishingly long neck, but also for the dramatic scientific rivalry that helped shape the history of paleontology. Today, the incomplete holotype specimen of Elasmosaurus, catalogued as ANSP 10081, remains the only specimen that scientists can confidently identify as belonging to this famous marine reptile. This historic fossil was once proudly displayed for visitors, but it is now carefully stored in a cabinet alongside other fragments that may be related to it. Even though it is incomplete, the specimen preserves an impressive collection of bones. It includes the paired premaxilla at the tip of the snout, part of the rear section of the right maxilla, 2 additional maxilla fragments still holding teeth, the front portions of the dentaries from the lower jaw, 3 more jaw fragments, and 2 skull pieces whose exact identities are uncertain. Most remarkable are the 72 neck vertebrae, including the atlas and axis, which supported the animal's extraordinarily long neck. In addition, there are 3 pectoral vertebrae, 6 vertebrae from the back, 4 sacral vertebrae from the hip region, 18 vertebrae from the tail, and several rib fragments. In the year 2013, researchers rediscovered an incomplete neck vertebra centrum that had been mentioned long ago by the American paleontologist Edward Drinker Cope, but was believed to have been lost. Its rediscovery confirmed that the total number of neck vertebrae should be revised from 71 to 72. However, the neck bones are not perfectly preserved. Over millions of years, Natural processes during decay and fossilization distorted them. Some vertebrae were flattened, shifted out of position, or compressed in unnatural ways, and certain parts were not fully prepared from the surrounding rock. In the year 1986, scientists completed a full three-dimensional reconstruction of the holotype skeleton, which is now displayed at the Academy of Natural Sciences of Drexel University. This cast brought the ancient reptile back to life in skeletal form. Later, the company Tribold Paleontology Incorporated created additional replicas for other museums. One such replica, displayed at the Fort Wallace Museum, measures about 12.8 meters in length, which is roughly 42 feet, giving visitors a striking sense of the animal's enormous size. Although Cope described and illustrated the shoulder and hip girdles of Elasmosaurus in the years 1869 and 1875, these important bones were reported missing from the collection in the year 1906 by the American paleontologist Samuel Wendell Williston. Cope had loaned these girdle elements to the English sculptor Benjamin Waterhouse Hawkins so they could be freed from the hard rock encasing them. At that time, Hawkins was working on an ambitious Paleozoic museum project in Central Park, where a life-sized reconstruction of Elasmosaurus was planned. This project was meant to be an American counterpart to his famous Crystal Palace dinosaurs in London. In May of the year 1871, tragedy struck when much of the material in Hawkins' workshop was destroyed by vandals for reasons that remain unclear. The broken pieces were buried, and it is very likely that the Elasmosaurus girdle bones were among the destroyed items. After this event, neither Hawkins nor Cope publicly discussed the loss of these fossils. In the year 2018, researchers Davidson and Everhart carefully reconstructed the chain of events leading to the disappearance. They suggested that a photograph and drawing of Hawkins' workshop from the year 1869 may show rock concretions on the floor that could have contained the unprepared girdle bones. They also discovered that early design sketches of the Paleozoic Museum originally showed Elasmosaurus with a long tail rather than a long neck, an idea that was later corrected. Based on all available evidence, they concluded that the girdle fossils were almost certainly destroyed in the workshop attack. In the year 1871, the American geologist Benjamin Franklin Mudge found additional fossils that may have belonged to the holotype, but these specimens have likely been lost. More plesiosaur fossils were later recovered near the original discovery site in the years 1954, 1991, 1994, and 1998. These included back vertebrae, ribs, belly ribs known as gastralia, and smooth stones called gastroliths that the animal may have swallowed. Because none of these bones overlapped with parts already known from the holotype, the American paleontologist Michael J. Everhart suggested in the year 2005 that they probably belonged to the same individual. He proposed that parts of the skeleton may have separated before burial. He also noted that a small polished stone lodged inside the neural canal of one tail vertebra might be a gastrolith based on its smooth surface. However, in the year 2007, the Colombian paleontologists Leslie Noe and Marcela Gomez Perez questioned whether the additional fossils truly belonged to the original specimen or even to Elasmosaurus at all. They pointed out that some missing bones might have been destroyed by weathering, overlooked during collection, or damaged during transport and preparation. They also emphasized that gastroliths were not recognized in plesiosaurs until 10 years after the original discovery, meaning early collectors might not have realized the importance of such stones. In the year 2017, researchers Sachs and Joachim Ladwig proposed that a fragmentary elasmosaurid skeleton discovered in the Upper Campanian deposits of Kronsmoor in Schleswig-Holstein, Germany, and housed in the Naturkunde Museum Bielefeld might actually belong to Elasmosaurus. Additional parts of this same skeleton are kept at the University of Hamburg and in private collections. When all pieces are considered together, the German specimen includes vertebrae from the neck, back and tail, finger bones known as phalanges, a tooth, limb elements, 110 gastroliths, and several fragments that cannot yet be identified. If confirmed, this discovery would extend the story of Elasmosaurus far beyond North America, adding a new chapter to the long and complicated history of this extraordinary marine reptile. Elasmosaurids were completely built for life in the ocean. Their bodies were smooth and streamlined, and they had long, strong paddles that show they were active swimmers. However, their unusual body shape likely limited how fast they could move. Their paddles probably worked in a way similar to oars on a boat, pushing through the water in firm strokes. Because of this rowing motion, the paddles could not twist much and were held stiff. Scientists have also suggested that plesiosaurs were able to keep their body temperature steady and high, a trait known as homeothermy. This would have helped them swim for long periods without tiring, even in cooler waters. A study published in 2015 concluded that movement was mainly powered by the front flippers, while the hind flippers helped with steering and keeping balance. Another study in 2017 suggested something even more interesting. The hind flippers may actually have produced 60% more thrust and worked with 40% greater efficiency when moving together with the front flippers. The paddles of plesiosaurs were so stiff and so specialized for swimming that they likely could not crawl onto land to lay eggs like modern sea turtles. Instead, they probably gave birth to live young in the water, similar to some sea snakes. Strong evidence for this idea comes from a fossil of an adult Polycotylus found with a single unborn baby preserved inside its body. Fossils also show that elasmosaurids were sometimes hunted by other predators. The upper arm bone of a young elasmosaurid was discovered with bite marks that matched the teeth of the giant shark Cretoxyrhina. In another case, the crushed skull of Eromangosaurus had tooth marks that matched the massive pliosaur Kronosaurus. These discoveries show that even these long-necked marine reptiles were not always at the top of the food chain. In the year 1869, the paleontologist Edward Drinker Cope compared the body and lifestyle of Elasmosaurus to that of a snake. He believed the main part of its spine was too stiff for much up and down bending because the tall bones along the back were packed closely together. Still, he imagined the neck and tail were very flexible. He described the animal lifting its snake-like head high above the water, curving its neck like a swan before diving for fish, or stretching it forward as it calmly floated. Modern research has changed that dramatic image. Scientists now believe Elasmosaurus could not lift much more than its head above the water. Its extremely long neck shifted its center of gravity behind the front flippers, making it difficult to raise the neck high unless it was in shallow water and resting part of its body on the sea floor. The neck was heavy, and the muscles and joints between the vertebrae allowed only limited movement. Because of this, it probably could not swim in one direction while turning its head sharply in another. The head and shoulders likely acted like a rudder, guiding the rest of the body. If the front part turned, the entire body followed. Cope also reported that the scales and teeth of 6 kinds of fish were found directly beneath the backbone of the original Elasmosaurus fossil. He believed these fish were its food. From those remains, he even named a new species of barracuda, Sphaerina carinata. The neck of Elasmosaurus could bend in ways that allowed several hunting strategies. One method may have been benthic grazing, which involved swimming close to the sea floor and using its head and neck to search through the mud for prey. Elasmosaurids may also have hunted in open water. They could pull back their necks and then strike forward quickly, or swing their heads sideways to stun prey with their long outward-pointing teeth. Their large skulls, strong jaw muscles, powerful jaws and long teeth suggest they were capable predators. Stomach contents show they ate animals ranging from about 30 centimeters to 2 meters long, including sharks, fish, mosasaurs, and cephalopods. It is possible that Elasmosaurus and its relatives quietly followed schools of fish from below. By staying hidden in darker water and slowly raising the head upward, they could approach prey without being seen. Their eyes were positioned on top of the head, allowing them to look directly upward. This forward-facing vision would have helped them judge distance and spot small prey. They likely swallowed their food whole, since their slender teeth were designed for gripping rather than tearing, and their skulls were not built to handle very large prey pieces. Although many elasmosaur fossils are found with stones in their stomachs, known as gastroliths, Elasmosaurus itself has only clearly been found with a single pebble lodged in one of the bones of its tail. A related animal, Styxosaurus, was discovered with broken fish bones and stones in its belly. The fish were identified as Encodus and other similar fish. Remarkably, the stones matched rock found about 600 kilometers away from where the fossil was discovered. Scientists have suggested that these stones may have helped grind food during digestion, added minerals, stored nutrients, or even helped control buoyancy in the water. Elasmosaurus is known from rocks belonging to the Sharon Springs member of the Upper Cretaceous Pierre Shale in western Kansas. These rocks date from about 80.64 to 77 million years ago. During that time, much of central North America was covered by a shallow inland sea known as the Western Interior Seaway. At its largest, this sea stretched from the Rocky Mountains to the Appalachian Mountains and was about 1,000 kilometers wide. Despite its vast size, it was not extremely deep, reaching only about 800 to 900 meters at its deepest points. Rivers from both the east and west flowed into this sea, bringing fresh water and large amounts of mud and silt. This created shifting river deltas along the coasts. The western shoreline changed often as sea levels rose and fell, and as sediment built up. The sea floor was soft and muddy, and very little sunlight reached the bottom. Even so, life was abundant. Large clams called Inoceramus covered the sea floor, often layered with oysters. Over centuries, their shells piled up beneath the mud, creating shelter for small fish. Other animals living in this sea included rudists, crinoids, squids, and ammonites. It was in this rich but dim underwater world that Elasmosaurus swam, hunted, and survived among both prey and powerful predators.